Europa, a frozen moon orbiting Jupiter, is one of the most intriguing worlds in our solar system. Beneath its smooth, icy crust lies an ocean more than twice as deep as Earth's, and it's a place where the conditions could be just right for life to exist. But what makes Europa even more fascinating is that we're on the brink of uncovering a lot more of its secrets. Multiple Europa missions have been launched and will, in the early 2030s, give us the most detailed look yet at this mysterious moon, peering through its icy shell to explore its hidden depths. Let's uncover Europa's strange surface features, its relationship with Jupiter, and its mysterious ocean that might just answer one of our biggest questions. Are we alone out there? The Forgotten Notes of Galileo, how Europa's identity was lost and found. In the early years of the 17th century, the world was on the brink of a scientific revolution, and the sky itself was revealing secrets long hidden from human eyes. Among the many figures in this era of discovery, one stands out above the rest. Galileo Galilei. With his groundbreaking invention of the telescope, Galileo opened up a new frontier for humanity, one that would forever change our understanding of the universe. On January 7, 1610, Galileo, using his improved telescope, made a remarkable discovery: 4 moons orbiting the giant planet Jupiter. These moons, later known as the Galilean moons, were unlike anything anyone had ever seen before. The discovery not only confirmed that celestial bodies existed beyond the Earth, but also challenged the long-held geocentric model of the universe, which placed Earth at the center of all things. As Galileo pointed his telescope toward Jupiter, he sketched the positions of these moons over the course of several nights, recording their movements with a precision that would later prove essential to our understanding of the solar system. The 4 moons he observed, Io, Europa, Ganymede, and Callisto, were so close to Jupiter that they appeared as small dots of light dancing around the planet. Galileo's sketches were simple yet revolutionary. They showed that the moons were in orbit around Jupiter, not the Earth. However, among the 4 moons Galileo identified, one, Europa, would have a much more complicated history. The moon was there, clearly visible in Galileo's drawings, but something strange happened in the years that followed. Early astronomers, as they continued to study Jupiter's moons, became fixated on the larger, more prominent ones, particularly Io and Ganymede, and Europa's identity became obscured in the rush of scientific attention. For many years, Europa was relegated to the status of an afterthought, its name and importance fading into the background. This confusion can partly be attributed to the way in which early astronomers miscounted or misidentified the moons. Galileo's sketches were crude by modern standards, and the technology of the time was not always capable of resolving the fine details needed to distinguish the moons from one another. To make matters worse, the discovery of Jupiter's moons came at a time when the concept of the solar system itself was still being defined. The scientific community was still debating whether the Earth was indeed the center of the universe, and Galileo's observations were controversial, to say the least. In addition to this, the Renaissance context in which Galileo worked was one of rapid intellectual change, but also of intense opposition from the church and traditional scholars. Galileo's findings challenged the established wisdom of the time, and his advocacy of the heliocentric model, proposing that the Earth orbited the Sun, was met with fierce resistance. Amid such tensions, the details of his astronomical work, including the discovery of Europa, were not given the attention they deserved. For some time after Galileo's initial sketches, it was not Europa, but the larger moons, especially Ganymede, that garnered more interest. Ganymede, being the largest moon in the solar system, was an obvious focal point for further study. Europa, by contrast, was smaller and less spectacular in appearance, making it more easily overlooked. Even as later astronomers, like Johannes Kepler, confirmed the existence of the Galilean moons and refined the understanding of their orbits, Europa remained an underexplored object in the field of astronomy. The moon was mentioned in subsequent astronomical texts, but it was often overshadowed by the more prominent members of Jupiter's entourage. As the years passed, Europa's significance was nearly forgotten. It wasn't until the 19th century that serious attention was once again directed toward this relatively obscure moon. By that time, the broader scientific community had come to accept the heliocentric model, and with it, the recognition that Jupiter and its moons were part of a much larger system than initially imagined. The rediscovery of Europa's importance came at a time when technological advancements had improved our ability to observe distant objects in the sky. The invention of more powerful telescopes, as well as advancements in mathematical modeling, allowed astronomers to revisit the Galilean moons with fresh eyes. In the late 1800s, astronomers like Wilhelm Herschel began to take a more detailed look at Europa. They observed its surface features, its faint shadow crossing Jupiter, and its unusual orbit, which seemed to indicate that Europa was more complex than initially thought. As the 20th century progressed, the development of space exploration technology, most notably the Voyager spacecraft, finally revealed Europa's true nature. By then, astronomers had come to understand that Europa was more than just another moon of Jupiter. Its surface, cracked and streaked with lines, suggested a hidden ocean beneath, fueling speculation about the possibility of life in its subsurface waters. In the 1970s, the Voyager missions provided the first close-up images of Europa, and the world took notice. These images showed a surface marked by large frozen plates that appeared to have been shifted or broken apart, as though something was pushing and pulling from below. Scientists began to realize that Europa might harbor the conditions necessary for life. With its subsurface ocean and an environment rich in chemicals, it seemed like the kind of place where life, as we know it, might be able to exist. Today, Europa's name is widely recognized, and it plays a central role in discussions about the search for extraterrestrial life. Yet, it is worth remembering that this moon's identity was nearly lost for centuries, only to be revived as technology advanced and our understanding of the cosmos deepened. Despite Galileo's careful observations and his pioneering work, Europa's identity as a unique celestial body was, for a time, obscured by the priorities and limitations of the era. But in the end, the quest for knowledge would always find a way to bring forgotten moons back into the light. Laplace's Resonance, the gravitational dance that warms Europa. As the centuries passed and Europa's name was revived in the scientific community, its importance grew not just because of its potential to harbor life, but because of the complex and fascinating forces that shaped it. One of the factors that make Europa such an intriguing object in the solar system is its unique relationship with the other moons of Jupiter. This relationship, known as Laplace's Resonance, plays a crucial role in keeping Europa's surface dynamic and potentially capable of sustaining an underground ocean. It also provides the energy that could be necessary for life to exist beneath its icy crust. To understand this, we need to step back in time and look at the complex mechanics of Jupiter's moon system. As we know, Jupiter has 4 large moons. These moons are locked in a delicate gravitational dance with the 3 innermost moons, Io, Europa, and Ganymede, following a pattern that is known as Laplace's Resonance. This resonance refers to a specific, repeating relationship between the moon's orbits. Europa, along with Io and Ganymede, shares a unique orbital arrangement where their orbital periods are linked in a 1:2:4 ratio. This means that for every orbit that Io completes around Jupiter, Europa completes 2 orbits, and Ganymede completes 4. This is a result of gravitational interactions between the moons that have been carefully fine-tuned over billions of years. Because of this resonance, the moons do not move in perfectly circular orbits. Instead, their paths are slightly elliptical or eccentric, meaning that their distance from Jupiter fluctuates as they orbit the planet. When Europa orbits Jupiter, its position in space is subtly affected by the gravitational forces exerted by Io and Ganymede. These forces tug on Europa, causing its orbit to stretch and compress slightly with each pass. This stretching and compressing, which happens every time Europa orbits Jupiter, results in what scientists call tidal forces. These tidal forces have a dramatic effect on Europa's interior. As the Moon's orbit fluctuates, the gravity from Jupiter and the other moons causes Europa to experience a slight wobble. This wobble, known as orbital eccentricity, is a crucial factor that helps to warm Europa from the inside. As Europa's orbit stretches and contracts, the Moon is subjected to varying amounts of gravitational pull. When the distance between Europa and Jupiter is at its closest point, the Moon is subjected to a stronger gravitational pull, and when it is farthest from Jupiter, the pull is weaker. This constant tug-of-war between the varying forces causes Europa to experience significant friction within its interior. This friction, which takes place deep beneath Europa's icy crust, generates heat. In fact, it is believed to be one of the primary sources of energy that keeps Europa's subsurface ocean from freezing solid. While the surface of Europa is covered by an icy shell, scientists believe that there is a vast ocean beneath, kept warm by the tidal heating. This ocean is thought to be in contact with the Moon's rocky core, and it may be one of the most promising places to search for signs of extraterrestrial life. The process of tidal heating works because, as Europa's orbit becomes slightly eccentric, its shape changes ever so slightly. The gravitational forces from Io and Ganymede create a continual stretching and compressing of Europa's shape, much like how the tides on Earth are caused by the gravitational pull of the Moon. However, the effects on Europa are far more dramatic. The constant flexing of its interior generates heat, much like how a rubber band warms up when it is stretched and twisted. One might think that this effect would be too small to have any real impact on the Moon's environment, but the forces involved are much stronger than we might expect. Europa's eccentric orbit is just enough to cause significant friction inside the Moon. The tidal heating is not uniform. Some parts of the Moon experience much more stretching and compressing than others. This results in the release of energy in the form of heat, which is then transferred to Europa's icy shell. In some places, the heat is enough to melt the ice, creating regions where the subsurface ocean can remain liquid, despite the freezing temperatures on the surface. This heating mechanism is thought to be so powerful that it could be one of the reasons Europa's surface appears to be geologically active. In 1995, NASA's Galileo spacecraft provided the first close-up images of Europa, revealing an icy surface that appeared to be broken into large puzzle-like plates. Some areas of the surface showed signs of stretching and cracking, suggesting that something below was pushing and pulling the ice. The heat generated by tidal forces could create the conditions necessary for life beneath Europa's ice. In some places on Earth, life has been found in extreme environments, such as deep beneath the ocean near hydrothermal vents. These ecosystems thrive in complete darkness and survive on the heat and chemicals released by the vents. Europa's subsurface ocean, kept warm by tidal heating, could offer a similar environment, one where life could potentially exist, hidden from the harsh conditions on the surface. Europa's orbital resonance also affects the other moons in the system. As Io and Ganymede exert their gravitational pull on each other and on Europa, their interactions create a delicate balance that has remained stable for billions of years. This gravitational dance, although it might seem chaotic at first glance, has been finely tuned over time. The orbital resonance between the three moons ensures that their orbits remain stable and that the tidal forces remain constant. This delicate gravitational dance, which has played out over billions of years, is one of the most remarkable examples of how the universe works in unexpected ways. A simple, repeating orbital resonance has led to the creation of a moon that might one day hold the answers to some of the biggest questions humanity has ever asked. Jupiter's magnetospheric grip on Europa's frozen soul. Jupiter, the largest planet in our solar system, is a colossal force of nature in more ways than one. Beyond its sheer size, its magnetic field is one of the most powerful in the solar system, an invisible yet dominant influence that stretches far beyond the planet itself. For Europa, this magnetic field has an important role in shaping its surface and environment. While Europa's orbit and its connection with other moons like Io and Ganymede give rise to the internal heating that warms its ocean, it is Jupiter's magnetospheric grip that constantly bombards Europa's frozen exterior with high-energy radiation. This radiation, while harsh and destructive, also plays a fascinating role in the Moon's surface chemistry, continually altering and renewing. Europa lies within the vast magnetic bubble known as Jupiter's magnetosphere. This is a region of space controlled by the planet's magnetic field, where charged particles from the Sun and other sources are funneled and trapped by Jupiter's magnetic forces. Unlike Earth's magnetic field, which shields us from much of this radiation, Jupiter's immense magnetic field envelops Europa, trapping high-energy particles that constantly rain down on the Moon's icy surface. These particles primarily consist of electrons and ions, including sulfur and oxygen ions that originate from the volcanic moon Io, as well as protons and electrons from the solar wind. The particles traveling through Jupiter's magnetosphere are not a mere nuisance. They are incredibly energetic and powerful, traveling at speeds that can approach 30,000 kilometers per second. As Europa orbits Jupiter, it plunges through this torrential rain of charged particles. As a result, the Moon's surface is continuously bombarded, with the most intense radiation hitting Europa's trailing hemisphere, the side that faces away from Jupiter. These particles, in turn, bombard the Moon's icy shell, shattering bonds in the molecules that make up the surface ice. On the one hand, this radiation is destructive. It can break apart the water molecules in the ice, leading to the formation of new compounds that were not present before. Over time, the surface of Europa is slowly being altered by this ongoing bombardment, with some areas being transformed into a mixture of new chemicals and minerals. One of the most notable effects is the creation of molecules like hydrogen peroxide, or H2O2, and other oxidizing compounds. These substances form when the radiation knocks electrons into the water molecules, splitting them and then recombining them into more complex molecules that wouldn't normally exist in the absence of such extreme energy. This process is not limited to just creating new molecules. It is also destructive in the sense that it continually erodes the surface. The radiation bombards the ice with such intensity that it causes the surface to slowly degrade, breaking it down into smaller particles and even creating tiny cracks in the icy shell. These cracks can allow heat and material from Europa's ocean to rise up, potentially supplying important nutrients to the surface. While this may seem like a harsh and unyielding environment, it also sets the stage for a continual renewal of surface chemistry. Europa's surface chemistry is constantly changing, and some scientists believe that this ongoing transformation could be critical for supporting life beneath the ice. In Earth's ecosystems, for example, hydrogen peroxide plays a key role in various chemical reactions. When combined with other compounds, it could potentially serve as a kind of energy source for hypothetical life forms in Europa's subsurface ocean. In fact, some researchers speculate that the hydrogen peroxide and other chemicals generated by the radiation could provide a source of energy for microbes, similar to how life on Earth relies on chemical processes near deep-sea hydrothermal vents. In addition to hydrogen peroxide, other compounds are also created by the radiation. These include sulfuric acid, which is thought to play a role in the chemical makeup of Europa's surface. The sulfur dioxide and other compounds from Io's volcanic plumes are carried by Jupiter's magnetic field and deposited onto Europa's surface. This sulfuric rain is another example of how Jupiter's magnetosphere plays an active role in shaping the chemistry of Europa, as the sulfur compounds combine with the Moon's icy surface to form new chemical structures. However, this radiation does not affect Europa in the same way it would affect a body like Earth. Earth's magnetic field, along with its atmosphere, acts as a protective shield, preventing much of the harmful radiation from reaching the surface. Europa lacks both an atmosphere and a strong magnetic field of its own, leaving it vulnerable to Jupiter's radiation. The constant bombardment of charged particles is not just a passive process. The energy from these particles can penetrate deep into the ice, triggering reactions in the subsurface and potentially influencing the flow of material from Europa's ocean to its surface. While we cannot yet say for sure how this process works, it's possible that the radiation contributes to the movement of water from the ocean below, allowing for the exchange of chemicals between the surface and the liquid world beneath. Scientists have long been intrigued by Europa's surface, which appears to be a fractured, icy landscape, with huge ridges, cracks, and valleys. These surface features are thought to be the result of a combination of tidal heating and radiation, which together create a dynamic, ever-changing environment. The continuous bombardment by charged particles, along with the heat generated by tidal forces, causes the ice to shift and crack, creating a constantly evolving landscape. Radiation alters the surface chemistry, while the chemical changes themselves might affect how the surface responds to forces like tidal heating. The presence of radiation-generated molecules could be crucial in understanding how Europa's ice shell behaves. If these molecules are incorporated into the surface ice, they might help to explain why some areas of Europa's surface appear to have been fractured and shifted in such a peculiar manner. Why Europa's orbit makes it a unique candidate for subsurface life. Europa's distance from the Sun places it at a relatively cold, inhospitable location in the outer reaches of the solar system. Situated about 628 million kilometers from the Sun, Europa receives only a fraction of the solar energy that Earth does. The average temperature on its surface hovers around -160 degrees Celsius, far colder than the freezing point of water. In these conditions, water should remain frozen, and any life on the surface would likely be unable to survive. The amount of energy produced by tidal heating, on the other hand, is substantial, and this energy flows into Europa's subsurface ocean, preventing the water from freezing solid. Europa's magnetic interaction with Jupiter further contributes to its potential habitability, as we've already discussed. But the magnetic interaction also has another effect, one that is less well understood, but potentially crucial to the stability of the subsurface environment. The interaction between Europa's icy surface and Jupiter's magnetic field creates an electrochemical environment that could be important for sustaining life in the Moon's ocean. Just as life on Earth uses chemical energy to survive in extreme environments, life on Europa could similarly rely on the chemical reactions triggered by Jupiter's magnetic field. Unlike moons or planets that are too close to their parent stars, where the energy from the Sun would lead to boiling oceans, Europa remains at a temperature where liquid water can persist in the subsurface. The constant movement and heat from tidal flexing ensure that the ocean is in a state of constant motion, with material from the deep ocean potentially being exchanged with the surface over time. Moreover, the ice shell above the ocean acts as an insulating barrier, protecting the water from the harsh conditions of space while also creating an environment in which chemical reactions can take place. The ice may provide a surface on which complex organic molecules can form. The movement of the ice shell could transfer materials, potentially replenishing nutrients and compounds that might help support microbial life. The unique combination of tidal heating, magnetic interaction, and orbital resonance means that Europa is not only a place where liquid water can exist, but also a place where conditions may be favorable for life. The heat from tidal flexing ensures that the ocean stays warm enough to support chemical reactions, while the magnetic field creates an electrochemical environment that might be important for sustaining life. These factors together make Europa one of the most intriguing places in the solar system when it comes to the possibility of life beyond Earth. Its conditions are remarkably different from those on Earth, yet the fundamental elements necessary for life, liquid water, heat and chemistry, are all present. For scientists, this makes Europa a prime target. Radiolysis on ice, how surface chemistry points to ocean secrets. Radiolysis occurs when high-energy radiation from Jupiter's powerful magnetosphere bombards Europa's surface. Charged particles, primarily electrons and protons, strike the water ice, breaking the chemical bonds that hold water molecules together. Water, or H2O, consists of two hydrogen atoms bonded to one oxygen atom. When radiation hits the surface, it splits these molecules, causing the hydrogen and oxygen atoms to break apart. This process releases the constituent atoms and creates new chemical species in the process, including molecular hydrogen, or H2, oxygen, or O2, and hydroxyl radicals, which are OH. These new molecules then either recombine to form different compounds or become trapped in the icy surface. The interaction of radiation with water on the surface can tell us a great deal about what lies beneath. For example, the hydrogen that is produced in radiolysis may not be native to the surface ice. Rather, it may have originated from the subsurface ocean. This provides scientists with a means of studying what might be happening underneath the crust, without having to drill through the thick ice. While much of the ice on Europa's surface is ancient, having been exposed to radiation for billions of years, there are indications that newer ice is also present. The chemical traces of hydrogen and oxygen found in the ice can give us clues about the composition of Europa's ocean and the materials that might be present there. The ocean beneath the ice is likely to be chemically rich, filled with dissolved gases and minerals that have been carried from Europa's rocky interior. The surface chemistry created by radiolysis could be an indication that there is an exchange of material between the surface and the ocean below, helping to maintain a dynamic relationship between the two layers. The process of radiolysis also plays an important role in the creation of new chemical compounds. Oxygen, one of the key byproducts of radiolysis, is particularly interesting. When the water molecules are split, oxygen can become trapped in the ice or released into space. The presence of oxygen on the surface of Europa is significant because it suggests that the ice is not entirely stagnant. Over time, this radiolytic process can lead to the formation of complex chemical compounds on the surface, which may act as a kind of fingerprint, revealing the history of the surface and the potential for more complex reactions occurring below. In fact, scientists believe that the process of radiolysis could play a crucial role in the formation of organic molecules on Europa. Organic compounds are the building blocks of life as we know it, and their presence on Europa could be an important indication that the conditions needed for life are present beneath the ice. Some of these organic compounds could be formed from the reactions of radiation with simple molecules like methane, aka CH4, or carbon dioxide, aka CO2, both of which may be present in the Moon's surface ice. Over time, these molecules could accumulate on the surface, providing a potential source of energy and raw materials for any life forms that might exist beneath the ice. By studying the surface chemistry, scientists can infer a great deal about the composition of the subsurface ocean and its potential for harboring life. For instance, the presence of molecular hydrogen could suggest that there are hydrothermal vents or other active geological processes happening within Europa's ocean. The radiation that strikes the ice not only breaks down water molecules, but also creates patterns and marks on the surface. These surface patterns, which include dark streaks and chemical gradients, provide another layer of information about how the Moon's surface is evolving over time. In a sense, radiolysis serves as a chemical messenger. The breakdown of water molecules and the subsequent release of hydrogen and oxygen act as clues, pointing to the presence of fresh material coming from beneath the ice. By examining the chemical byproducts of radiation and understanding how they interact with the ice, researchers are gradually piecing together a picture of Europa's subsurface environment. Each fragment of hydrogen, each trace of oxygen, tells a story of a dynamic world with an ocean teeming with potential waiting to be explored. Brown-banded ice. Europa's plains are adorned with unusual streaks and patches, colored brown and rusty red. These striking discolorations of brown banded ice stand out against the Moon's otherwise stark, pale white icy landscape. These color anomalies raise questions about the processes shaping Europa's surface and the chemical interactions occurring there. The rust-colored bands and patches are a signal that there is more happening on Europa than meets the eye. This discolored ice does not behave like the ordinary pure water ice found elsewhere on the Moon's surface. Instead, the ice shows signs of chemical transformation, likely caused by some interaction between the surface and the environment. Several theories exist to explain this discoloration, but two of the most prominent ideas involve salt deposits and sulfur compounds. One theory suggests that the brownish stains and rusty streaks come from salt deposits, specifically magnesium sulfate salts. Europa's ocean is believed to contain various salts, and these could be ejected through cracks in the ice as the surface is flexed and reshaped by tidal forces. These salts might then settle on the surface, creating the rust-colored patches. When the salt interacts with radiation from Jupiter's magnetosphere, it could cause chemical reactions that result in a brownish or reddish tint. This theory connects the surface discolorations to the deeper subsurface ocean, implying that there is a link between the ocean and the Moon's surface chemistry. The idea of salt deposits is further supported by the fact that some of the discolored patches are located near cracks and fissures in Europa's ice shell, places where material from the ocean below might seep up through the icy crust. This exchange between the surface and the subsurface is not unique to Europa. Similar interactions have been seen on Earth, particularly in areas like hydrothermal vents or in environments with salt water. The salts rising from the ocean beneath Europa's icy shell could, over time, settle on the surface and contribute to the distinct brownish bands and patches that scientists observe. The salt hypothesis helps explain why these color anomalies tend to appear near areas of geologic activity, where the ice is more likely to crack and allow for material from below to escape. However, another competing theory suggests that the rusty streaks on Europa's surface may not come from salts, but from sulfur compounds originating from Io. Io's eruptions eject vast amounts of sulfur and sulfur dioxide into space. Once it reaches Europa, this sulfur-rich material could settle on the surface and interact with the ice, causing the formation of the reddish or brown streaks seen across Europa's plains. The sulfur compounds may undergo chemical changes due to radiation and extreme temperatures, contributing to the discoloration observed. The sulfur hypothesis is supported by the fact that the color anomalies on Europa's surface seem to be more pronounced in certain areas, particularly those that are more exposed to Jupiter's magnetosphere. This material could then interact with the surface, either directly or through a combination of processes like radiation, to create the distinctive color patterns seen on the Moon's icy crust. The sulfur theory emphasizes the broader interconnectedness of the Jovian system, suggesting that the chemistry of Europa's surface is influenced not only by the Moon's own geology and ocean, but also by the interactions between the moons of Jupiter. While the salt and sulfur theories both provide compelling explanations for Europa's brown-banded ice, the truth may lie in a combination of both factors. After all, Europa is not a static world. The forces at work beneath the ice create cracks and fractures that allow for the exchange of material. This exchange could bring up not only salts, but also gases and other compounds, including sulfur. Once these materials reach the surface, they may interact with radiation from Jupiter's magnetosphere, leading to the formation of the brown and rusty streaks that are seen on Europa's plains. While the exact origins of Europa's brown-banded ice remain a mystery, it is clear that the discolorations are the result of complex chemical processes. The brown streaks and rusty patches on Europa's plains are not merely superficial, they are part of the larger story of the Moon's geologic and chemical evolution. The silent plumes, searching for geysers without visual confirmation. In 2012, the Hubble Space Telescope, operating in ultraviolet light, provided evidence of what appeared to be faint plumes of water vapor erupting from Europa's surface. These plumes were spotted near the Moon's south pole, where cracks and fractures in the icy shell could allow material to escape. The Hubble team used a method called stellar occultation, where the Moon passed in front of a distant star, to look for any changes in the star's light caused by the water vapor. The data seemed to suggest that Europa was indeed venting material into space. This discovery led to widespread excitement, as it suggested the possibility of an active, dynamic surface, a world where material from the subsurface ocean might be escaping into space. However, while these observations hinted at the presence of plumes, they were not definitive proof. The water vapor seen by Hubble was faint, and the resolution of the telescope was not high enough to provide clear, direct images of the plumes. There was still no conclusive evidence that plumes were indeed present, and scientists remained cautious about interpreting the data. The observations did not show a clear, repeating pattern, and no plumes were directly caught in the act of erupting. In the absence of visual confirmation, scientists could only speculate about the nature of the plumes and whether they were a regular feature of Europa's behavior, or more of a transient event. The challenge of directly observing plumes on Europa is compounded by the fact that geysers, if they exist, are likely to be short-lived and highly transient. This is where the difficulty lies. Unlike some other moons, such as Enceladus, where geysers have been observed regularly over time, Europa's potential plumes could be fleeting and elusive. In 2005, the Cassini spacecraft made a historic discovery on Saturn's moon Enceladus, confirming the presence of plumes erupting from the moon's south pole. These plumes were not only visually confirmed, but they were also sampled by Cassini's instruments, which identified the composition of the material being ejected into space. The geysers on Enceladus have been seen numerous times, offering scientists an excellent opportunity to study their behavior and the processes driving them. In contrast, Europa's suspected plumes are much more difficult to capture. Part of the problem is Europa's distance from Earth and the relative rarity of opportunities to observe it in the right conditions. With its constantly shifting icy surface and complex interactions with Jupiter's magnetic field, Europa is a more challenging target for observation. These transient plumes, if they exist, could be difficult to catch, even with the most advanced telescopes. In addition to the challenges of observing Europa's surface directly, there are also technical limitations in the instruments used to study the Moon. Hubble, for instance, has provided valuable data, but its resolution in ultraviolet wavelengths is not sufficient to resolve individual plumes. Other telescopes, including those operating in infrared and optical wavelengths, also face challenges in detecting the faint signals that would be associated with water vapor escaping Europa's icy surface. Europa's surface is cold and dark, and any plumes would need to be detected against a backdrop of low light and subtle changes in the Moon's atmosphere. This makes it difficult to discern the exact nature of the observed phenomena and to rule out other explanations, such as cloud cover or atmospheric effects. Moreover, the suspected plumes are thought to be highly localized. Scientists believe that if Europa does have geysers, they would likely be concentrated at specific points, particularly near the Moon's south pole, where there are large fractures in the ice. These fractures could act as pathways, allowing water and other material from Europa's subsurface ocean to escape into space. However, because these plumes are so localized and sporadic, they would only be visible during specific observation windows. If they do exist, these geysers could provide valuable information about the Moon's ocean. The material that erupts from these plumes would be a direct sample of the ocean beneath Europa's icy crust. If water, salts, or organic molecules were found in these plumes, it would offer crucial insights into the chemical composition of Europa's ocean and the possibility of life thriving beneath the ice. The detection of such materials would be an exciting breakthrough, as it would allow scientists to study Europa's subsurface without needing to drill through its thick ice shell. The lack of direct confirmation of Europa's plumes has not stopped scientists from continuing to study the Moon in hopes of detecting them in the future. The Europa Clipper mission, launched in 2024, will provide new opportunities to observe the Moon in more detail. One of the key goals of the mission is to study Europa's icy shell and investigate whether plumes exist. Europa Clipper will fly multiple close passes of Europa, using a suite of scientific instruments to gather data on the Moon's surface, atmosphere, and subsurface. The spacecraft will be able to take more detailed measurements of Europa's surface features and look for signs of active plumes. Additionally, Europa Clipper will have instruments capable of analyzing Europa's surface chemistry and atmosphere in ways that previous missions could not, increasing the chances of detecting geyser activity. In addition to Europa Clipper, future missions to Europa may include landers or probes that could sample material directly from the surface or from any plumes that may be present. These missions could provide the most direct evidence of Europa's geysers and help scientists determine the composition of the material being ejected from the Moon. For now, though, the mystery of Europa's plumes remains unsolved. The challenges of observing such fleeting and transient activity, combined with the technical limitations of current instruments, have made it difficult to confirm whether Europa's surface is truly erupting with geysers. This search highlights the complexities of studying distant worlds and the limitations of our current technology. While we have made significant strides in understanding Europa's surface and its potential for life, there is still much to learn. Whether the geysers are a real feature of the Moon or a product of transient events remains a mystery, but the ongoing exploration of Europa will continue to provide new insights into this fascinating world. When salt turns blue, spectroscopic evidence for sulfates and chlorides. Spectroscopic data collected by various space telescopes and spacecraft reveal that Europa's surface contains salts, specifically sulfates and chlorides, that absorb light in specific ways, creating subtle hues of blue and green. The process of spectroscopic analysis works by measuring the way light interacts with the surface or atmosphere. Each substance absorbs and reflects light in unique ways, depending on its molecular structure. When a beam of light strikes an object, some wavelengths are absorbed, while others are reflected. By studying the pattern of absorbed and reflected light, scientists can identify the types of materials present, even if those materials are invisible to the human eye. This is precisely what scientists do when they study Europa's surface. By looking at the light that reflects off the Moon's icy shell, they can determine the chemical composition of the surface, including the presence of salts. Salt compounds like sodium chloride, which is just common table salt, sodium sulfate, magnesium sulfate, and others, are particularly important in this context because they have unique spectral fingerprints, specific wavelengths of light that they absorb. When light from the Sun strikes Europa's surface, it interacts with these salts, and the resulting light that reflects back to telescopes and spacecraft contains clues about the salts present. Different salts absorb light at different wavelengths, and this helps scientists figure out which salts are on the surface. One of the most interesting findings from these spectroscopic observations is that Europa's surface shows signs of both sulfates and chlorides, each contributing to the subtle blue or green hues seen in some areas. Sulfates like magnesium sulfate and sodium sulfate absorb light in certain parts of the spectrum, giving rise to blue or greenish tones in the reflected light. These color anomalies aren't just decorative, they represent important chemical processes that have occurred on Europa's surface and give us a glimpse into the nature of the Moon's ocean below. For example, sodium sulfate is a salt commonly found in environments where water is present, and it has a very distinctive spectroscopic signature. When scientists observe this signature, they are looking at a substance that likely formed in liquid water, which means that the presence of sodium sulfate suggests that liquid water, whether from the subsurface ocean or from ice that has melted and refrozen, has interacted with the surface. This is crucial because it hints at the possibility that Europa's ocean could be chemically similar to Earth's oceans, containing salts that might support life. Similarly, magnesium sulfate, another salt found on Europa's surface, absorbs light in ways that create distinct spectral features. Magnesium is an abundant element, and when it reacts with sulfur to form magnesium sulfate, the resulting compound can indicate that Europa's ocean contains not just water, but other chemical elements that could be critical to life. The presence of such salts could also hint at the chemical processes happening beneath Europa's icy shell. If these salts are forming on the surface, it may be because the ocean beneath is rich in minerals, providing the necessary conditions for life to flourish, if such life exists. The subtle blue or greenish hues that are seen in spectroscopic data can tell us about the salinity, acidity, and chemical makeup of the ocean. This type of analysis also provides clues about how these salts reached the surface in the first place. Some scientists believe that Europa's ocean could be in direct contact with the icy shell, meaning that materials from the ocean may be transported up through the ice and deposited on the surface. Other theories suggest that the salts may have been brought to the surface through the Moon's tectonic processes, where the ice crust is cracked and then reformed. The presence of certain types of salts could indicate that the ocean is undergoing a process of mixing and movement, perhaps driven by tidal forces or other energy sources. This makes the study of Europa's salts an important part of understanding its geologic and oceanic history. Life, as we know it, depends on water, and the chemical environment of that water plays a critical role in supporting or hindering biological processes. By studying the salts on Europa's surface, scientists can gain insights into the chemical composition of the subsurface ocean, increasing the chances of finding life on this frozen moon. Linei labyrinths, charting Europa's global fracture network. Europa's icy surface is marked by an intricate network of lines, cracks, and patterns. Among these surface features, the most striking are the Linei, long, dark fractures that stretch across Europa's surface for thousands of kilometers. These fissures are not merely surface blemishes. They are the result of complex processes beneath the ice, acting as a window into the dynamic forces at play within Europa's icy shell. The term Linei refers specifically to linear features that are darker than the surrounding ice, giving them a distinctive appearance. These cracks are typically several kilometers long and can vary in width, but they often run for distances far greater than typical surface fractures. They're seen across Europa's entire surface, from the equator to the poles, and they seem to form a global network that crisscrosses the Moon's frozen landscape. These long dark lines stand out against the icy plains, and their appearance is often tied to a process known as brittle failure. When the ice shell of Europa is subjected to stresses, the ice begins to crack. As these fractures widen, darker material from beneath the surface may seep through, creating the distinctive linei that we see today. These cracks represent large-scale structural deformations that span vast distances. Unlike smaller pits or jumbled terrains which might indicate localized stress or impact events, the Linei suggest a global process of tectonic or convective motion within the icy shell. The fact that the Linei appear in such a regular, global pattern suggests that the ice shell is responding to forces from beneath, likely originating from the ocean below. Tidal forces create stresses on Europa's ice shell, causing it to stretch and crack in ways that produce these long fractures. While there are numerous smaller cracks, pits, and ridges scattered across the surface, the Linei represent a larger, more coordinated response to the tidal forces Europa faces. They are a global phenomenon, and their long dark lines cut across the surface with a network-like structure. In some places, the Linei appear to intersect, forming a complex web of fractures that stretches across the Moon. In other areas, the Linei appear as long, straight cracks that run for hundreds of kilometers without interruption. These networks of fractures suggest a highly organized, systematic process of ice deformation. The dark color of the Linei is also significant. The darker regions within the fractures may indicate that material from beneath the ice is seeping up to the surface, possibly due to the movement of ice and the interaction with the ocean below. As the ice shell cracks and moves, materials such as salts, minerals, and even liquid water may be brought to the surface, staining the ice and creating the darker streaks that define the linea. The Linei also provide important clues about the thickness and behavior of Europa's icy shell. The cracks themselves can range in depth, with some Linei appearing relatively shallow, while others cut deep into the surface. This variation suggests that the ice shell is not uniform in thickness across Europa's surface. In some regions, the ice may be thinner, allowing for greater movement and deformation, while in other areas, the ice could be thicker, providing more resistance to cracking. Some scientists believe that the ocean beneath Europa's ice shell may be in constant motion, with convection currents and tidal forces driving the movement of both the ocean and the ice above. These forces could help to explain the way the ice shell fractures and deforms. The fractures in the ice could provide pathways for material to move between the surface and the subsurface ocean. These fractures could serve as channels for nutrients, minerals, and other essential ingredients that might support life. The Linei could also provide a mechanism for heat exchange, allowing warmth from Europa's interior to escape to the surface. By analyzing these long, dark cracks, scientists hope to gain a deeper understanding of Europa's geological history and the forces that shape this enigmatic moon. The Linei may be just one part of Europa's complex and mysterious surface, but they are a crucial piece of the puzzle that could unlock the secrets of this frozen moon. The mystery of Lenticuli. Are they rising blisters or sunken scars? Lenticuli are small, round hills or pits, often scattered in clusters across Europa's surface. Despite their unassuming size, ranging from a few hundred meters to a couple of kilometers in diameter, the lenticuli have puzzled scientists for years. Their unusual shape and distribution hint at underlying processes that are not immediately obvious. Lenticuli can appear in various forms, either as small, raised mounds or as depressions that sink into the surface. The raised lenticuli can give the appearance of tiny hills, while the sunken ones look like pits or craters. They are most noticeable in areas where the surrounding terrain is relatively flat, which makes these features stand out against the otherwise smooth, icy plains. Their regularity and spatial distribution suggest that they are the result of some kind of geological process, not random occurrences or impacts from space. However, scientists are still debating exactly what that process might be, and there are two main theories that attempt to explain the lenticuli's formation. The first theory is that the lenticuli are the result of diapiric activity, essentially the upward movement of material from Europa's interior. The term diapiric comes from a geological process where less dense material, such as ice, rises through denser material, much like a buoyant object floating to the surface of a liquid. In this case, the idea is that warmer ice, possibly from the subsurface ocean or heated by tidal forces, rises through the overlying colder layers of the ice shell. As the ice pushes upwards, it forms the raised mounds we observe as lenticuli. This process would likely occur in regions of the ice shell where there is significant internal heat and where the ice is relatively weak. The heat would be coming from tidal forces. The ice beneath the surface may be less solid and more mobile in these areas, allowing for the movement of warmer ice to rise toward the surface. When this ice breaks through, it creates the raised, hill-like structures of lenticuli. The upward movement could be slow and gradual, leading to the formation of these small, isolated features over long periods of time. The second theory about the origin of lenticuli focuses on the possibility of collapse over melting pockets of water or slushy ice beneath the surface. According to this theory, lenticuli form when pockets of warmer, partially melted ice or liquid water exist beneath the surface layer of solid ice. As the surrounding ice becomes weakened, potentially due to the tidal stresses Europa experiences, these pockets of liquid or slush cause the overlying ice to collapse inward. In this scenario, the lenticuli would appear as depressions as opposed to raised mounds, and would be the result of the ice shell sinking into these melting regions. The sinking could occur gradually, leaving behind circular pits or depressions that mimic the lenticuli's shape. One of the key differences between this theory and the diapiric model is that the lenticuli formed by collapse would represent areas of subsidence rather than areas of upward movement. Instead of ice pushing up from below, the surface would be drawn down into the space left by the melting or retreating ice beneath. This could occur in areas where there is more extensive melting, possibly due to localized heating or the influence of the ocean below the surface. If Europa's ocean is indeed active and dynamic, this could lead to pockets of water or slush migrating closer to the ice shell, causing local thinning and eventual collapse. The result would be the creation of the sunken lenticuli, which would look like pits or depressions in the surface. Both of these theories offer a plausible explanation for the origin of lenticulae, and it's possible that both processes could be occurring simultaneously in different parts of Europa's surface. In some areas, diapiric ice blobs may be rising to the surface, creating raised mounds, while in others, the ice may be collapsing over pockets of liquid, creating depressions. This dual mechanism could help explain the varied appearance of lenticuli across Europa's surface, where some features appear as raised mounds, while others are sunken. It's also worth noting that these two processes are not mutually exclusive. In fact, they may even interact with one another, as the movement of ice in one area could influence the dynamics of nearby regions. One of the challenges in understanding lenticuli is their small scale. Unlike the massive fractures and ridges found across Europa's surface, which are easily visible even from space, the lenticuli are much smaller and require a closer look to be fully appreciated. The features are often just a few hundred meters across, and their subtle nature makes it difficult to study them in detail. However, recent high-resolution images from spacecraft like NASA's Galileo and Hubble have allowed scientists to begin mapping the distribution of lenticuli and investigating their characteristics. These images have revealed that lenticuli are not evenly spread across Europa's surface, but instead tend to cluster in certain regions. By analyzing these patterns, scientists can start to infer the underlying processes that are creating these features and determine whether they are the result of diapiric activity, collapse, or a combination of both. If the lenticuli are indeed caused by diapiric activity, then they may be evidence of heat and movement within Europa's interior. The rising ice could indicate the presence of a warm, active ocean below the surface, where tidal heating is creating conditions for liquid water to exist. If the lenticuli are the result of collapse over pockets of liquid water or slushy ice, then they could suggest that the subsurface ocean is not only active, but also undergoing changes in temperature and composition. In either case, the lenticuli provide important clues about the dynamic processes that are shaping Europa. Europa's chaos terrains, shattered plates from a restless underworld. On Europa, there are vast regions where the surface looks as if it has been shattered into countless pieces, like the broken tiles of a grand mosaic. These are the chaos terrains, an area of fractured and disjointed ice blocks that seem to have been scattered and then rotated or tilted in different directions. The chaos terrains draw comparisons to the way large plates of Earth's crust can shift and collide to create rugged, fault-ridden landscapes. The chaos terrains often appear in regions where the ice has been broken up into irregular jigsaw-like pieces. These blocks can vary greatly in size, from a few kilometers across to much larger expanses. Some blocks appear to have been tilted or rotated, while others have shifted positions relative to each other, creating an eerie and disordered landscape. The term chaos aptly describes the disorder seen in these regions. There's no neat pattern, no uniformity, just a complex jumble of broken and disturbed pieces. The underlying forces responsible for this chaotic surface structure are linked to tidal flexing. In areas where the ice shell is weak or has been subjected to particularly intense tidal forces, the ice may fracture and become displaced, leading to the formation of chaos terrains. A notable feature of the chaos terrains is the way in which the ice blocks appear to have been moved or tilted, creating a disordered and fractured landscape. Some blocks are tilted at steep angles, while others are rotated as though they've been twisted out of their original position. In certain areas, these blocks appear to have sunk into the underlying ice, creating depressions or pits where the ice has been displaced downward. In other areas, the blocks seem to have been pushed upward, creating raised areas where the fractured ice has been pushed out of the way. This movement of the ice creates a surface that looks nothing like the smooth plains found in other parts of Europa. Linei are often arranged in parallel or curving patterns, creating a more ordered geometric look compared to the disordered chaos terrains. The linei suggest a different type of force at play, stretching and pulling of the ice, rather than the disintegration and jumbled movement seen in chaos terrains. Similarly, while lenticuli are thought to form either through diapirism or the collapse of ice over pockets of melted material, they do not exhibit the same large-scale disruption as chaos terrains. Instead, lenticuli are isolated, small-scale features that stand out in a much more orderly manner. They can appear as raised hills or as depressions, but their regularity and the smaller scale of their formation make them stand apart from the disordered surface seen in chaos terrains. Despite these differences, chaos terrains, linei, and lenticuli are all connected by the dynamic processes taking place beneath Europa's icy surface. The chaos terrains are believed to be the result of localized, intense heating beneath the surface that causes the ice to become weakened, allowing the crust to break apart. The tidal flexing from Europa's orbit around Jupiter plays a significant role in this heating. The chaos terrains are the ultimate expression of this intense stress and deformation. While the exact mechanism behind the disruption of the ice remains unclear, it is likely that the fractures are linked to the interplay of tidal forces and the internal heating of the Moon. One key feature of chaos terrains is the presence of floored regions, where the ice blocks are surrounded by a smooth, dark material. This material is believed to be a combination of water or slushy ice from below the surface, which has risen up and filled in the gaps between the broken ice blocks. The ocean may be pushing against the underside of the ice shell, contributing to the movement of the ice and helping to create the chaotic fractures that characterize these terrains. The appearance of chaos terrains also varies depending on their location on the Moon. In some regions, the ice blocks appear to be relatively small and closely packed, creating a fine-grained, densely fractured surface. In other areas, the ice blocks are much larger and the fractures between them are more widely spaced. This variation in the size and spacing of the blocks suggests that the forces acting on the surface may be uneven, with some areas of Europa experiencing more intense tidal flexing than others. This uneven distribution of stresses could help explain why chaos terrains are not evenly spread across the surface of the Moon, but tend to appear in specific regions, often near the equator. Scientists are still trying to determine the exact mechanisms that cause the ice blocks to move and shift. Are these movements caused purely by tidal flexing, or is there another process at work, such as the rising of liquid from Europa's ocean or the collapse of ice beneath the surface? How do these disruptions in the surface tie into the larger picture of Europa's geological activity? To answer these questions, scientists continue to study the chaos terrains in more detail, using high-resolution images and data. Each piece of the jigsaw-like puzzle is a small fragment of a much larger mystery, one that may one day help unlock the secrets of Europa's icy crust. Thermal anomalies in the ice shell, hotspots without volcanoes. Europa's surface, though largely frozen, has revealed some curious features that suggest there are areas of elevated temperature beneath the surface, places where the ice is unexpectedly warm. These warm patches, detected by infrared instruments aboard spacecraft like Galileo, stand out against the otherwise cold, frozen landscape. They hint at localized sources of heat within Europa's icy shell, yet they do not appear to be associated with the dramatic eruptions of cryovolcanoes, those icy volcanoes that have been detected on moons like Enceladus and Triton. Instead, these thermal anomalies point to a subtler but still intriguing kind of heating within the Moon. The thermal anomalies seen on Europa are typically small regions, where the ice temperature is higher than what would be expected given the usual conditions on the surface. These warmer patches are not scattered haphazardly across the entire Moon. Rather, they appear in specific, localized areas, which suggests they are tied to particular features or processes beneath the ice. The infrared data obtained by spacecraft show that these patches of heat are not large enough to be explained by the usual heating mechanisms, such as sunlight or internal friction from tidal forces alone. This suggests there may be something more going on beneath the surface that is driving these localized warm areas. One of the more puzzling aspects of these thermal anomalies is that they don't seem to be associated with any clear venting activity. On other icy moons, like Enceladus, researchers have observed plumes of water vapor and ice erupting from the surface, which are directly linked to warm areas where liquid water or slushy ice might be forcing its way through cracks. However, on Europa, there is no clear evidence of such plumes or cryovolcanic eruptions in the regions where these thermal anomalies are detected. There are no visible vents, no large geysers shooting material into space, and no significant surface disturbances that one might expect to see in the presence of an active cryovolcano. Despite the lack of visible eruptions, the infrared data suggests that heat is still being generated and escaping through the ice shell in these areas. It's as if there are hot pockets beneath the ice that are radiating heat directly upward, but in a much more subtle and less violent way than what we might see in more active cryovolcanoes. These warm patches could represent areas where the ice is thinner or weaker, allowing heat to escape more easily. Alternatively, they could indicate localized pockets of liquid water or slushy ice that are transferring heat from below the surface. The presence of heat in these areas might be a sign that there is still some activity beneath Europa's ice shell, possibly even areas where the ice is melting or transitioning into a less rigid state. Internal heating by tidal flexing may not be uniform across the entire Moon. Some areas of the ice shell may experience more intense flexing than others, leading to localized patches of higher temperatures. These hotspots could be the result of ice becoming thinner in certain regions, allowing heat to more easily escape. Or they could reflect the movement of warmer material from below. Another possibility is that the thermal anomalies are related to the cracking or shifting of ice, which could create pathways for heat to flow more freely from the subsurface. These shifts could be linked to the complex system of fractures and ridges that crisscross Europa's surface. In these regions, heat may be flowing upward through the ice without necessarily resulting in large-scale eruptions or visible surface activity. The fact that these thermal anomalies are not associated with cryovolcanic vents is significant because it helps differentiate the processes occurring on Europa from those on other moons with similar icy surfaces. On other moons, the presence of plumes is a clear indicator of active cryovolcanism, where heated water or ice is forced through cracks in the surface. The lack of such plumes suggests that the heating is occurring in a different way. Instead, the heat appears to be rising more slowly and steadily through the ice, without being released in dramatic bursts. This heat could be the result of convective processes occurring within the ocean, where warm water rises toward the ice shell and transfers heat to the surface. If this heat is concentrated in specific areas, it could explain the thermal anomalies detected by infrared observations. Alternatively, the anomalies might be related to diaparism causing localized heating. If future missions can target these warm regions, they might be able to collect valuable data that could reveal more about the Moon's internal processes. The floating raft hypothesis, plate tectonics of the icy kind. Among the many hypotheses about how this icy world works, one is the idea of floating rafts of ice. This theory suggests that Europa's ice shell might behave in a way similar to tectonic plates on Earth, though in a very different icy context. Instead of being rigid and unmoving, the ice could be floating over a more pliable layer, allowing large segments to move and shift like rafts on water. In many ways, this raft hypothesis borrows from the well-known principles of plate tectonics. On Earth, tectonic plates move across the planet's surface, driven by the heat from the core and the forces generated by the mantle beneath. These plates can slide, push against one another, and even break apart, creating mountains, earthquakes, and volcanoes. While Europa doesn't have the same kind of active molten mantle beneath its ice as Earth does, the basic concept of rigid plates moving over a softer layer still seems plausible. The idea is that the icy shell of Europa is not a single solid sheet of frozen water, but a collection of plates that shift and move across the surface, driven by forces beneath them. Europa's ice shell is believed to be between 15 and 25 kilometers thick, which is significant but still relatively thin compared to the size of the Moon itself. The vast subsurface ocean would be crucial for allowing the ice shell to move. If the ice were directly in contact with the ocean, the two could potentially slide against one another, creating a situation where the ice could move more freely, much like how tectonic plates slide over the Earth's molten mantle. The idea is that the ice could raft over the ocean, with different sections of the ice shell floating independently, much like large rafts floating on water. One of the features that supports this idea is the presence of large, broken, and rotated blocks of ice that we see across Europa's surface. In areas where the ice shell appears to have fractured, the pieces seem to be moving relative to one another. Some of these pieces appear to have rotated, shifted, or been pushed around in ways that suggest the ice is behaving like a set of plates, not a single unyielding surface. These movements might be caused by the forces exerted by the subsurface ocean or by tidal stresses from Europa's orbital interaction with Jupiter. If the ice shell was simply rigid, such movements would be impossible without causing significant disruptions to the surface. The raft hypothesis suggests that beneath the surface, the ice plates float atop a much softer, more pliable layer. This could be a layer of slushy, partially liquid water, or perhaps a mixture of water and ice that is less rigid than the overlying shell. It's this underlying softness that could allow the ice plates to move and shift. In essence, Europa's ice could be acting much like a set of large rafts drifting over an ocean of water beneath it. This movement would likely be very slow and gradual, but it could still have a significant impact on the surface features we observe today. The large cracks and ridges that slice through the ice seem to have a clear pattern, often appearing in linear and coherent shapes. If Europa's ice shell were moving in a way that mimicked the movement of tectonic plates, these linear features might be a natural result. The movement of the ice plates could create stretching, cracking, and bending, forming the ridges and fractures that make up the global network of Linei and other surface features. Over time, as the ice plates continue to shift, the surface of Europa would look like a constantly evolving puzzle, with pieces being rearranged and changed by the forces at work beneath. One of the key aspects of this hypothesis is the need for a soft, pliable layer beneath the ice shell. Without this, the ice would be unable to move in the way that the raft hypothesis suggests. Some scientists think that the subsurface ocean could act as this soft layer. The ocean would not be uniform, of course. There could be areas where the water is more slushy or partially frozen, providing a different kind of frictional environment that could allow the ice to slide more easily. If this ocean is in contact with the bottom of the ice shell, it could play a crucial role in the movement of the ice above it, providing the necessary lubrication for the ice plates to drift and shift over time. In contrast, the more chaotic terrains observed on Europa, like the regions with jumbled ice blocks and disordered fractures, suggest a very different kind of motion. These regions are often highly fractured and appear to have experienced rapid localized shifts that don't necessarily fit the organized patterns seen in the larger, more coherent plate movements. While these chaotic terrains could be the result of tidal forces and other internal stresses, they are not consistent with the idea of large, coherent plates moving in unison. Instead, these areas might reflect the more random forces that can also act on Europa's surface, resulting in broken and displaced pieces of ice. The raft hypothesis could also help explain some of the features observed in Europa's ridges and cracks. In many places, the ice appears to have been pulled apart, creating large stretches of open space between the separated pieces. This kind of movement is consistent with the idea of plates shifting and sliding over one another, much like how the Earth's tectonic plates pull apart in areas like the Mid-Atlantic Ridge. As the ice stretches and moves, it could create these large fractures that define the surface. The fact that the fractures are often aligned in certain patterns further supports the idea of coherent movement, as these patterns would be unlikely to form if the ice were simply breaking randomly. One potential challenge to the raft hypothesis is the question of how the ice could move without disrupting the entire shell. If the ice is floating over an ocean, as the hypothesis suggests, it would likely be subject to forces from both the subsurface ocean and Jupiter's tidal forces. These forces could cause the ice to move in complex ways, and it's still unclear whether the ice could move smoothly without tearing apart entirely. The raft hypothesis would need to explain how the ice remains in large, coherent plates rather than fracturing into smaller pieces or collapsing under the forces at work. While the theory is still being tested and refined, it has already helped scientists think about Europa's surface in a new light. Europa's ocean pressure. How deep is too deep for life? Europa's vast, salty ocean is potentially teeming with the conditions to support life. But beneath that thick, frozen crust, the pressure is immense. As we look deeper into this world, the question becomes, how deep is too deep for life? To understand the pressure at the bottom of Europa's ocean, we need to start with a basic calculation of the weight exerted by the ice above. The ice shell of Europa is thought to be between 15 to 25 kilometers thick. As this ice sits on top of the ocean, it creates an immense amount of pressure due to the sheer weight of the frozen water. Pressure increases by approximately 1 atmosphere, or ATM, for every 10 meters of water depth. This is why the deep ocean on Earth, especially around the Mariana Trench, experiences crushing pressures that can reach over 1,000 times the pressure we experience at sea level. On Europa, the situation is similar, but with the added layer of ice. The exact pressure at Europa's ocean floor would depend on how thick the ice shell is, but let's consider a relatively average thickness of around 20 kilometers. Taking the density of ice into account, it's estimated that the weight of Europa's ice would add a pressure of about 200 megapascals, or MPa, at the ocean floor. This pressure is equivalent to nearly 2,000 times the pressure we experience at sea level on Earth. For comparison, the deepest parts of the Earth's oceans, like the Mariana Trench, reach a pressure of around 110 megapascals. So Europa's ocean floor would experience pressures far greater than anything we know on Earth. This kind of extreme pressure raises important questions about whether life could survive in such an environment. On Earth, life has found ways to thrive in deep, high-pressure environments. These habitats are some of the most extreme environments on the planet, with temperatures exceeding 400 degrees Celsius and pressures similar to those found at Europa's ocean floor. Creatures like giant tube worms and specialized bacteria have evolved to withstand these conditions. But what about Europa? Europa's ocean is different in several key ways. For one, its environment is far more isolated. The ice shell above could act as a thick barrier, cutting off the ocean from sunlight and preventing any natural heat sources from reaching the water. This isolation could make it harder for life to find the energy it needs to survive, especially in comparison to Earth's deep ocean ecosystems, where sunlight isn't needed, but heat from the planet's core provides a continuous energy source. However, the idea of life surviving in such an extreme environment is not out of the question. We've seen examples of life on Earth that can withstand unimaginable pressure. Deep-sea organisms live in conditions where the weight of the water above is far greater than what we experience on land. Some of these creatures are able to survive by adapting their biological processes to handle the crushing pressure. Their bodies are built differently from those of shallow water organisms, and they often rely on chemical energy. The ocean on Europa is believed to be salty, which could also help life survive. Salinity lowers the freezing point of water, keeping the ocean liquid despite the extreme cold of the icy shell. In a salty environment, the chemical reactions needed for life to thrive may also be more likely to occur. On Earth, saltwater ecosystems are home to a wide variety of life, from microscopic bacteria to large fish and mammals. The salt in Europa's ocean could provide a similar environment, allowing for a rich array of chemical reactions that might sustain life. But there are also challenges to life in Europa's ocean. On Earth, deep-sea organisms are adapted to high pressure, but they still rely on certain temperature and chemical conditions to survive. If Europa's ocean floor is too cold or too chemically barren, it might be hard for life to find a foothold. The pressure might not be the only obstacle to life. The lack of available nutrients or energy sources could also be a significant barrier. One of the key factors that could allow life to survive is the potential presence of hydrothermal activity. If there are areas of the ocean floor that are geologically active, with hydrothermal vents releasing heat and chemicals into the water, this could provide the necessary conditions for life to survive. These vents could also act as an energy source for microorganisms. There is also the possibility that the pressure at Europa's ocean floor might not be as much of an obstacle as it seems. Life on Earth has evolved in all kinds of extreme environments, from the bottom of the deepest oceans to the frozen tundra. If organisms could adapt to the crushing pressure on Earth, it's conceivable that they could also adapt to the pressures found on Europa. For example, deep-sea organisms have evolved to withstand the crushing forces of the deep ocean by altering the way their cellular membranes function. They have specialized proteins that help them maintain their structure despite the high pressure. It's possible that life on Europa could use similar adaptations to survive under the immense pressure of the ocean floor. Europa's ocean is still a subject of intense study and speculation. While we don't yet have all the answers about what lies beneath its ice shell, we do know that the conditions are extreme. The pressure at the ocean floor is one of the key factors that will determine whether life could survive on Europa. If life does exist on this icy moon, it would likely be very different from life on Earth. Europa's ocean may hold secrets that could help us understand the resilience of life in the most extreme conditions, and perhaps one day we may find evidence that life has indeed found a way to survive beneath the ice. Salt, acid, or alkali, probing the chemical nature of Europa's hidden sea. The pH of Europa's ocean, the measure of its acidity or alkalinity, could be crucial in determining what kind of chemistry is taking place beneath the ice. On Earth, the pH of a body of water has a significant impact on the types of organisms that can thrive there. Life as we know it has evolved in the narrow range of neutral pH around 7, though some organisms have adapted to survive in more extreme conditions, from the highly acidic lakes in volcanic regions to the alkaline waters of certain soda lakes. In Europa's ocean, the pH could be anywhere along this scale, from acidic to neutral to alkaline, and the pH of this ocean could directly influence the types of chemical reactions that occur, and in turn, the possibility of life. The most likely source of the chemicals that would determine the ocean's pH is the interaction between water and the rocky surface of Europa's ocean floor. Scientists have long speculated that Europa's ocean is in contact with a rocky sea floor. This could create a dynamic environment where minerals are dissolved into the water, and chemical reactions take place that shape the nature of the ocean's chemistry. If the ocean is in contact with basic minerals, the pH could be alkaline. If the minerals are acidic, the ocean would likely be more acidic. Some scientists believe that Europa's ocean could be highly alkaline, driven by the interaction between the water and silicate minerals from the rocky sea floor. These minerals, rich in compounds like magnesium and calcium, could dissolve into the water and raise the pH, making the ocean more basic. This would make sense because alkaline environments are known to foster certain types of chemical reactions that are important for life. On Earth, for example, certain types of bacteria thrive in alkaline conditions, and life in extreme environments has evolved to take advantage of the chemical gradients that exist between acidic and basic regions. On the other hand, Europa's ocean could be interacting with more acidic minerals, such as sulfur compounds from the interior of the Moon or from volcanic activity on Io. These sulfur compounds could react with the water and lower the pH, creating a more acidic environment. An acidic ocean would be very different from an alkaline one, and this could have major implications for the types of reactions that could occur. Acidic environments are known to break down certain organic molecules and could make it more difficult for life to form. However, life on Earth has evolved in some very acidic environments, such as the acid pools in Yellowstone National Park, where bacteria thrive in water with a very low pH. So while an acidic ocean would present challenges, it wouldn't rule out the possibility of life. Another consideration is that Europa's ocean might not be purely acidic or alkaline, but could have a more neutral pH. This would be ideal for life as we know it, as the wide range of chemical reactions that are necessary for life can occur most efficiently in neutral conditions. If Europa's ocean were neutral, it would likely be a much more hospitable environment for the types of complex chemistry required for life. But neutrality is not a certainty. Given the uncertainty surrounding the specific mineral composition of Europa's ocean floor, it's still unclear which direction the pH will tilt. A basic or neutral ocean would likely support more diverse chemical reactions, particularly those involving carbon, nitrogen, and sulfur. These are the building blocks of life on Earth, and life on Europa, if it exists, might depend on similar chemical processes. For example, in a basic or neutral environment, carbon dioxide could be converted into organic molecules, similar to how plants use photosynthesis on Earth. Similarly, nitrogen could be fixed into usable compounds by microorganisms, a process that is essential for the creation of amino acids and proteins. In an acidic ocean, these same reactions might be hindered. Acidic conditions could break down complex organic molecules before they have a chance to form. On Earth, life has adapted to many extreme conditions, including acid-laden environments, so it's possible that if life were to exist in Europa's acidic ocean, it could take a very different form. For example, organisms that thrive in acidic environments on Earth tend to rely on alternative forms of energy. They may utilize sulfur compounds, iron, or other chemicals found in abundance in extreme conditions. If Europa's ocean were acidic, life might have adapted to use these chemicals in much the same way. Scientists are not only studying the mineral composition of Europa's surface and theorizing about its ocean's chemistry, but they are also looking for clues in the surface features of the Moon. The surface chemistry, particularly in the regions where salts and other chemicals have been deposited, could give scientists a hint about the ocean's pH. One intriguing idea is that the pH of Europa's ocean might not be uniform. Just as there are varying levels of salinity in Earth's oceans, Europa's ocean could have localized regions with different pH levels. In some areas, the ocean might be alkaline, while in others, it could be acidic. This would create a more complex and dynamic environment, and could offer more opportunities for chemical reactions to take place. The models we have so far are based on the limited information available, and there is a lot more to learn. Hydrothermal vents. Without Earth, could Europa have black smokers? On Earth, some of the most fascinating ecosystems exist in the deep ocean, far from the reach of sunlight. These ecosystems thrive around hydrothermal vents, often called black smokers. These vents spew out warm, mineral-rich water from beneath the ocean floor, providing the energy and nutrients necessary to support entire communities of organisms that don't rely on sunlight for survival. Instead, these life forms rely on a process known as chemosynthesis, where chemicals such as hydrogen sulfide are used as an energy source. Given the similarities between Europa's ocean and the deep oceans of Earth, could Europa have something akin to these black smokers? Europa, like Earth, likely has a rocky seafloor. While we can't directly observe what's happening on the ocean floor, there are several clues that suggest that seafloor vents might be a possibility. It's possible that Europa's internal heat is concentrated in certain areas, particularly at the ocean floor. where it could drive hydrothermal activity. If there are regions where the ocean floor is warmer, it could create conditions similar to the ones found near Earth's black smokers. In these areas, water could be heated beneath the seafloor and forced upwards, carrying with it dissolved minerals from the rock below. These minerals would be rich in elements that are essential for life, such as sulfur, methane, and hydrogen. When this mineral-rich water reaches the cold, high-pressure environment of the ocean, it could create a black smoker effect, with dark plumes of material rising from the ocean floor. In fact, scientists have already found evidence suggesting that Europa's ocean might have the right conditions for such vents. The Moon's surface is covered in fractures, and some of these could be the result of tectonic activity beneath the ice. These cracks might also serve as channels through which warm water from the ocean floor could rise, much like the chimneys found at Earth's hydrothermal vents. If this warm water does indeed reach the surface, it could provide clues about the composition of the ocean and the types of minerals present in Europa's seafloor. On Earth, the minerals and chemicals spewed out by black smokers are essential for fueling chemosynthetic life. These vents are home to strange organisms that rely on the chemicals coming from the Earth's crust for energy rather than sunlight. The most common chemical used in these ecosystems is hydrogen sulfide, a compound that is toxic to most life forms, but can be used by specialized microbes to produce food. These microbes form the foundation of the food chain in these vent ecosystems, supporting entire communities of organisms. If Europa has similar hydrothermal vents, it could potentially harbor similar ecosystems. Scientists believe that the Moon's ocean may contain a variety of minerals and chemicals that could be used by life forms, including hydrogen sulfide, methane, and other compounds. In such an environment, chemosynthetic organisms might thrive, using these chemicals to fuel their metabolism. However, there are challenges in determining whether Europa could truly have hydrothermal vents. One of the key factors to consider is Europa's rock composition. On Earth, black smokers are typically associated with oceanic ridges, where tectonic plates are spreading apart, allowing hot rock from the mantle to rise and interact with seawater. Europa's rocky seafloor may not have the same geological features as Earth's mid-ocean ridges, so scientists must consider whether there is enough geological activity to support such vents. While Europa doesn't have plate tectonics in the same way Earth does, it still experiences a kind of tectonic activity, where the icy shell can flex and move. This motion could lead to the formation of fractures or faults in the sea floor, where heat from the ocean's interior could escape, similar to how seafloor vents on Earth are formed. If these fractures are connected to areas of heightened geothermal activity beneath the ocean, it could create an environment where hydrothermal vents could form. In addition, Europa's ocean may have a different composition than Earth's oceans, which could affect the types of chemicals available for chemosynthesis. The specific chemistry of Europa's ocean and the presence of these chemical compounds would play a key role in determining whether life could survive near hydrothermal vents. The possibility of hydrothermal vents on Europa, providing warmth, nutrients, and energy to support life, makes the Moon even more compelling as a potential haven for life in the universe. As we continue to explore Europa with future missions, the possibility of discovering black smoker-like vents and chemosynthetic ecosystems may not be as far-fetched as it once seemed. Pioneers at a distance, what Voyager and Galileo told us in hindsight. The Voyager spacecraft, launched in the 1970s, and later the Galileo orbiter in the 1990s, were pioneers that expanded our understanding of Europa. These missions, while groundbreaking, were limited in their scope and capability, and in hindsight, they only scratched the surface of Europa's many secrets. The Voyager missions, Voyager 1 and Voyager 2, were primarily designed to study the outer planets of the solar system, with a particular focus on Jupiter. The spacecraft passed through the Jupiter system in 1979, capturing the first detailed images of its moons. These flybys provided humanity's first look at Europa, revealing a moon covered in a smooth, icy surface. Voyager's images showed a world that seemed almost too perfect. No large craters or obvious signs of impact. Europa's surface was marked by broad dark streaks and lighter patches, which scientists initially struggled to interpret. While Voyager was able to show us Europa's surface and provide some preliminary data, the images were distant and blurry. The spacecraft passed by the moon so quickly, at a speed of about 58,000 kilometers per hour, that the data they captured was limited to brief snapshots, too fleeting to answer the deeper questions about Europa's interior or the exact processes shaping its surface. In the wake of the Voyager missions, Europa remained a distant, enigmatic world. There was speculation about the possibility of an ocean beneath its icy surface, but no clear evidence to support it. The mysteries of Europa's ice shell and what lay beneath continued to linger, unanswered. While the Voyager spacecraft gave us crucial initial insights into the appearance of Europa, they weren't equipped to investigate the Moon in any real depth. It wasn't until the 1990s, with the launch of the Galileo spacecraft, that we began to gain a much more detailed understanding of Europa. Galileo, which entered orbit around Jupiter in 1995, had the capability to study the moons of Jupiter in far greater detail than its predecessors. This mission was designed to explore the Jovian system for a prolonged period, allowing for sustained observations and data collection. Galileo provided the first detailed study of Europa's icy surface, revealing the complex features that we recognize today. These observations were a huge leap forward in our understanding of the Moon. The Galileo mission, however, faced its own set of challenges. While it was able to map the surface in greater detail, the spacecraft's instruments were limited in their ability to penetrate Europa's thick ice shell or study its subsurface in any meaningful way. Galileo's most impressive achievement was its close flybys of Europa, where it captured high-resolution images and performed various scientific experiments. The mission helped confirm that Europa's surface is dominated by water ice and revealed signs of tectonic activity, such as the long dark cracks that suggest the ice shell was undergoing some sort of dynamic movement. These findings gave strong indications that Europa's interior might be active and possibly home to a subsurface ocean, but once again, direct evidence of an ocean or any sort of active hydrothermal environment remained elusive. One of the most important surprises revealed by the Galileo mission was the discovery of Europa's magnetic field. By studying Europa's interaction with Jupiter's immense magnetic field, scientists were able to infer the presence of a conductive, salty ocean beneath the icy surface. This was one of the most compelling pieces of evidence, suggesting that Europa might indeed have an ocean beneath its surface. The magnetic field data suggested that the Moon's interior was electrically conductive, which could only occur if there were a subsurface ocean with high levels of salt. This discovery prompted new models of Europa's structure, where the ocean was now seen as a major component of the Moon's internal composition. Despite these significant breakthroughs, the spacecraft's inability to study Europa's ocean directly meant that many of the ideas about Europa's internal composition remained speculative. Was the ocean deep or shallow? Was it chemically rich enough to support life? How did the ocean interact with the seafloor? And the most important question of all, could life exist in this distant frozen ocean? Galileo's limited ability to gather data on the subsurface left scientists yearning for more detailed exploration. While it had provided a wealth of information about Europa's surface features, the oceanic mysteries of the Moon remained unresolved. The mission demonstrated that Europa was not just a frozen world, but one that might harbor an active and potentially habitable environment beneath its icy shell. However, the data gathered by Galileo alone wasn't sufficient to confirm this theory. The legacy of these early missions was invaluable, but it became clear that more dedicated missions were needed. Voyager and Galileo had paved the way, But to truly understand Europa and its potential for harboring life, a new kind of exploration was required, one that could focus specifically on Europa's unique characteristics. The drive for further exploration of Europa was galvanized by the realization that these early missions had merely scratched the surface of what could be learned. As scientists pored over the data from Voyager and Galileo, they were struck by how much more there was to discover about Europa. The next generation of missions would have to be equipped with better instruments and a more focused goal: to unlock the mysteries of Europa's ocean and its potential for life. In hindsight, the Voyager and Galileo missions provided the essential foundation for all subsequent studies of Europa. The Voyager flybys, although brief, revealed Europa's intriguing surface features and raised the question of whether an ocean lay beneath. Galileo's long-term study confirmed that Europa was a geologically active world. These early discoveries sparked interest in Europa as a potential site for extraterrestrial life and set the stage for future missions. The technology of these early missions was limited by the standards of today, and they faced significant hurdles in their attempts to study Europa in detail. Yet despite these limitations, these pioneers provided a glimpse into a world that was, at the time, utterly alien to us. Their discoveries continue to inspire and guide current research into Europa, as the mission planners of today build on the groundwork laid by these early explorers. And it's this spirit of curiosity that will continue to propel us toward the next big step in our journey to understanding Europa. The Galileo paradox: why the mission that visited Europa left so many questions. One of the major issues Galileo faced was the intense radiation environment around Jupiter. The gas giant's powerful magnetic field accelerates charged particles, which form a highly energetic radiation belt around Jupiter. Europa, orbiting within this radiation zone, was particularly vulnerable to this bombardment of high-energy particles. Galileo was affected by this radiation. The spacecraft's sensitive instruments were damaged by the radiation. These instruments, over time, began to degrade, limiting their ability to take accurate measurements. The radiation exposure essentially scorched many of Galileo's sensors, leading to the loss of some key data over the course of its mission. This radiation-induced degradation of Galileo's instruments was a significant blow to the mission's ability to perform long-term, detailed studies of Europa. Some of the most critical data that could have been used to probe the Moon's surface and subsurface were compromised, leaving scientists with a patchwork of incomplete results. While the spacecraft was able to provide tantalizing glimpses into Europa's surface features, the full picture was elusive. Galileo's orbit around Jupiter meant that it approached Europa from different angles during its flybys, and at times, the spacecraft's line of sight to the Moon was less than ideal. This limited the resolution of some of its observations. There were times when the spacecraft was not positioned in such a way that it could study Europa's most critical areas in detail. The flybys of Europa were brief, sometimes lasting only minutes, and the spacecraft didn't always have enough time to collect the data needed to form a complete picture of the Moon. The spacecraft also experienced periods when communication with Earth was cut off, or when it was unable to transmit data back due to various technical issues. These interruptions often coincided with the most crucial parts of the mission, such as close flybys of Europa, leading to gaps in the data that made it difficult for scientists to piece together the full story of Europa's surface and interior. Without a complete set of observations, it was impossible to confirm or rule out many of the theories that had been proposed. Despite these setbacks, Galileo did achieve significant successes in its exploration of Europa. However, while these findings were groundbreaking, they only raised more questions about Europa's hidden ocean. How deep was the ocean? What was its composition? Was it chemically rich enough to support life? These were just some of the critical questions that Galileo's data hinted at, but did not answer definitively. The spacecraft's inability to directly study Europa's ocean left a gap in our understanding that has persisted to this day. The spacecraft's data raised more possibilities than it could definitively prove, and many of the mysteries of Europa remain just out of reach. The data gaps and instrument limitations of Galileo showed the need for more advanced, dedicated missions that could study Europa in greater detail, especially in terms of its subsurface ocean. While the mission provided valuable insights, it also demonstrated how much we still have to learn. The lost promise of the Jupiter Icy Moons Orbiter. In the early 2000s, a bold and ambitious mission was being planned by NASA and its international partners, one that had the potential to revolutionize our understanding of the icy moons of Jupiter, especially Europa. This mission, known as the Jupiter Icy Moons Orbiter, or JIMO, was envisioned as a cutting-edge spacecraft designed to explore Europa, Ganymede, and Callisto in unprecedented detail. Unlike any previous mission, JIMO would have been powered by advanced nuclear propulsion, a technology that would allow the spacecraft to venture far from Earth and explore these distant moons for years. But despite the promising start and high expectations, JIMO would ultimately fall victim to budget cuts and shifting priorities, never making it past the planning stages. JIMO was conceived at a time when the scientific community was increasingly excited about the potential of Europa. The Moon had already been identified as one of the most likely places in our solar system to harbor life. NASA's decision to focus on Europa alongside Ganymede and Callisto reflected the growing recognition of these moons as key targets for astrobiology. But to study these moons in detail, a new kind of spacecraft was needed, one that could travel farther, move faster, and stay in operation long enough to gather meaningful data. What set JIMO apart from other missions was its planned use of nuclear propulsion, a technology that had been developed and tested on a small scale but never used on an interplanetary mission. The concept of nuclear-powered spacecraft was based on the idea that traditional chemical rockets wouldn't provide enough thrust to send a probe to the outer reaches of the solar system, especially with the scientific payloads that JIMO would carry. Instead, JIMO would use a nuclear reactor to generate power, which would drive an ion engine, an incredibly efficient form of propulsion that could work over long distances and provide continuous acceleration. This would allow the spacecraft to travel to Jupiter's moons faster than any previous mission and remain in operation for years, sending back detailed data about Europa's surface, subsurface, and potential ocean. The promise of JIMO was immense. It would have had the ability to conduct detailed surveys of Europa's ice shell and its subsurface ocean. The mission could have explored the moon's surface in high resolution, mapping out the chemical composition of its icy crust, identifying potential plumes of water vapor, and studying the magnetic fields that hinted at the presence of a subsurface ocean. This would have been the first mission capable of not only investigating Europa's surface in depth, but also examining the interactions between the moon's ice shell and the underlying ocean. JIMO would also have been able to perform an extensive series of flybys of Europa, Ganymede, and Callisto, gathering data on each of these moons in a way that no other mission had done before. The spacecraft would have studied the moon's magnetic fields, radiation environments, and icy surfaces with unprecedented sensitivity. Its propulsion system would have enabled it to stay in orbit around these moons for extended periods, offering a level of detail that would have been impossible for flybys conducted by missions like Galileo or the Voyager spacecraft. This ability to remain in the vicinity of these moons for extended periods would have provided invaluable insights into the ongoing processes at work on Europa. But as promising as JIMO was, it was also a costly mission. The development of nuclear propulsion systems, the spacecraft itself, and the complex scientific instruments it would have carried would have required an enormous investment of time, money, and resources. In the early 2000s, as NASA moved forward with planning JIMO, the cost of the mission continued to rise, and the agency faced increasing pressure to justify its budget. Budget cuts, shifting priorities, and the growing costs of other space programs led to a difficult decision. JIMO was cancelled in 2005, before it had even been built. The cancellation of GMO was a significant blow to those who had hoped it would pave the way for future missions to the outer planets. While the cancellation was partly due to the high cost, it also reflected the political and practical realities of space exploration. The mission was ambitious, but it was also seen as a massive leap into the unknown. Nuclear propulsion was still unproven for large-scale missions, and many of the technological aspects of GMO would have required significant advancements to succeed. Despite its potential, GMO was ultimately deemed too risky, too expensive, and too far removed from NASA's other priorities at the time. The cancellation of GMO marked the end of one grand vision for Europa exploration, but it also led to a shift in focus. Rather than a single massive spacecraft with nuclear propulsion, NASA turned to smaller, more practical missions that could still achieve important scientific goals without the need for experimental technology. The Europa Clipper mission is the direct result of this shift. While it does not have the advanced nuclear propulsion system that GMO promised, Europa Clipper is a highly capable spacecraft that will use conventional chemical propulsion to conduct a series of flybys of Europa. With a suite of advanced instruments designed to study Europa's surface, subsurface, and potential ocean, Europa Clipper aims to answer many of the questions that GMO would have addressed, albeit in a more practical and cost-effective way. While the Europa Clipper mission will not be able to linger around Europa as long as GMO would have, it will still be able to perform a detailed series of flybys, collecting data from different angles and times to piece together the puzzle of Europa's hidden ocean. In many ways, the Europa Clipper mission can be seen as a scaled-down version of the promise of GMO, a mission that will carry out many of the same goals, but with more conventional propulsion and a more focused scientific approach. While GMO would have been an incredibly ambitious and groundbreaking mission, the practicalities of space exploration led to its cancellation. However, the loss of GMO has not diminished our desire to explore Europa. Instead, it has refocused our efforts on a mission that is still capable of answering key questions about this fascinating moon. The story of GMO serves as a reminder of the risks and rewards of space exploration. The vision of GMO represented the cutting edge of space technology and the potential for truly groundbreaking discoveries. However, practical realities ultimately led to its cancellation. The radiation challenge: how instruments survive Jupiter's wrath. Jupiter is one of the most hostile environments for spacecraft in our solar system. Its immense magnetic field generates a radiation environment around its moons that is far beyond what we experience here on Earth. Europa is no exception to this radiation barrage. The radiation here is intense, and any spacecraft designed to explore Europa has to contend with it, from the very moment it enters the planet's magnetic influence to the point it leaves. Understanding how this radiation works, how it affects the electronics on spacecraft, and the strategies employed to protect sensitive instruments is a crucial part of any mission to the Jovian system. Radiation around Jupiter comes from a variety of sources, but most notably from its powerful magnetosphere. It traps charged particles, which are accelerated to near-light speeds and bombard anything within the magnetosphere, including Europa. These high-energy particles form the core of the radiation environment. They can penetrate spacecraft shielding and damage the sensitive electronics on board, making it necessary to develop specialized strategies to protect the instruments and ensure their functionality throughout the mission. The radiation intensity around Europa is not uniform. As the Moon orbits Jupiter, it passes through regions of varying radiation intensity. The Moon is located within Jupiter's inner radiation belt, meaning that the radiation here is especially concentrated. In fact, the radiation flux at Europa's surface can be hundreds of times stronger than the radiation levels found in low Earth orbit, where astronauts are exposed to harmful radiation from the Sun and cosmic rays. Over time, this high radiation exposure can cause serious damage to the delicate components of a spacecraft, such as sensors, electronics, and wiring, which may result in the loss of data, reduced mission lifespans, or even complete mission failure. The main concern with radiation exposure is the effect it has on the spacecraft's electronic components. These systems, which are responsible for controlling the spacecraft's navigation, communication, and science instruments, rely on delicate circuits that are vulnerable to radiation. High-energy particles can interfere with the flow of electricity through these circuits, leading to malfunctions, loss of data, or complete failure of key systems. The problem is compounded by the fact that radiation is not a single burst of energy, but a continuous bombardment over time, gradually degrading the components and increasing the likelihood of failure. One of the primary strategies for dealing with this radiation is shielding. While there is no way to completely eliminate the radiation exposure, it is possible to reduce its effects by surrounding the spacecraft's most sensitive components with protective materials. This shielding is typically made from materials that are good at absorbing or scattering high-energy particles, such as aluminum, titanium, and special radiation-absorbing composites. The thickness and placement of the shielding are carefully calculated to protect the spacecraft's electronics without adding too much weight. These materials act as a barrier, reducing the number of particles that reach the spacecraft's sensitive electronics, thus minimizing the risk of damage. However, even with shielding, certain components on a spacecraft may still need additional protection. In particular, sensors and instruments used for scientific measurements are especially vulnerable to radiation damage. These sensors are designed to collect data from Europa's surface, subsurface, and environment, but they rely on highly sensitive detectors that can be easily disrupted by radiation. To address this challenge, many of the scientific instruments on Europa missions are hardened to withstand the intense radiation environment. This hardening process involves modifying the design of the sensors and electronics to make them more resilient to radiation-induced damage. This might include using radiation-resistant materials, employing redundant systems that can take over if one fails, and programming the instruments to automatically shut down during particularly intense radiation bursts, allowing them to recover once the radiation levels subside. One notable example of this type of radiation-hardened equipment is the Europa Clipper mission's imaging systems. These systems are designed to capture high-resolution images of Europa's surface, studying the Moon's icy shell, potential water plumes, and other features that may provide clues about its ocean. Given the harsh radiation environment, the Europa Clipper's cameras and spectrometers have been specifically designed to tolerate prolonged exposure to Jupiter's radiation. This means they have been equipped with protective shielding and, in some cases, have been built using electronics and materials that can resist the destructive effects of high-energy particles. Aside from shielding and hardening, another strategy to combat radiation is to time the spacecraft's exposure. While this approach is less effective in reducing radiation, it is still important in limiting the amount of time a spacecraft spends in the most dangerous areas. For example, mission planners carefully design spacecraft trajectories to minimize time spent in Jupiter's high radiation zones. For the Europa Clipper mission, this means using gravity assists from Jupiter's moons and flybys to maximize science returns while minimizing radiation exposure. The spacecraft's trajectory will take it through the outer regions of the magnetosphere, where radiation is less intense, allowing it to collect data while limiting its exposure to damaging radiation. By designing instruments and electronics with redundancies in place, such as backup systems that automatically kick in when the primary systems fail, the spacecraft can continue to operate for as long as possible despite the effects of radiation. On some missions, components are even tested for their ability to withstand radiation before they are installed on the spacecraft. These tests simulate the radiation environment the spacecraft will encounter, ensuring that the electronics can survive the intense conditions they will face on their journey to Europa. Despite these efforts, even with the best shielding and engineering practices, radiation remains one of the biggest challenges for missions to Europa. The radiation environment here is unlike any other in the solar system, and it can wear down even the most advanced technology over time. This is why careful planning is required at every stage of mission design, from spacecraft construction to long-term operations. The goal is not only to protect the spacecraft's instruments, but also to ensure that they continue to collect valuable data for as long as possible, enabling scientists to learn as much as they can about Europa and its potential for habitability. Europa Clipper's eyes and ears, how instruments will decode the ice. While Europa Clipper will be zipping past Europa at speeds reaching up to 20 kilometers per second, its suite of instruments will be working tirelessly to gather a broad spectrum of data from the surface and beneath the icy crust. Each instrument is critical, contributing a unique perspective on the Moon's composition, structure, and processes, while also complementing the others to provide a holistic understanding. The Clipper's ice-penetrating radar, known as REASON, or Radar for Europa Assessment and sounding ocean to near surface, is one of the mission's flagship instruments. This radar is capable of transmitting powerful radio waves through the icy surface and measuring the echoes that bounce back from different layers beneath. The main goal of this radar is to map Europa's ice shell in high resolution, providing detailed images of the thickness and structure of the ice, and potentially identifying pockets of liquid water trapped beneath. While the ice shell is thought to be about 10 to 30 kilometers thick, we do not know much about its internal structure. REASON will help reveal whether the ice is in one solid sheet or if it is fractured into separate plates. It can also detect if there are pockets of liquid water trapped beneath the ice, which could be crucial in understanding the potential habitability of Europa. With its radar technology, REASON will be able to see through the surface ice, providing a view of the Moon's internal structure, much like how radar on Earth is used to map underground layers, or how radar is used in some archaeological digs to peer beneath the ground. One of the reasons REASON is so powerful is that it uses two different frequencies of radar waves, each of which provides unique information about the ice and ocean layers beneath. The radar operates at both a low frequency and a higher frequency, with each wavelength optimized for detecting different features. The dual frequency setup allows REASON to penetrate the ice at various depths. The low-frequency radar waves are the ones that can penetrate deeper into the ice, reaching the deeper layers of Europa's icy crust. These waves have longer wavelengths, which allow them to travel through the ice without being absorbed or scattered too much. By measuring how these low-frequency signals are reflected, REASON can map out the thickness of the ice shell. It can also identify large structures within the ice. If there is a subsurface ocean or liquid water within the ice, the low-frequency radar will detect the boundary between the ice and the liquid, offering one of the most direct ways to measure the ocean's depth and extent. On the other hand, the higher frequency radar waves are better suited for detecting smaller structures near the surface. These waves have shorter wavelengths and are better at identifying fine details in the upper layers of ice. For example, they can reveal the fine structure of the ice itself, such as the presence of different ice types or changes in the composition of the surface. The higher frequencies are also sensitive to smaller fractures, changes in ice density, and variations in surface features, providing insight into the more detailed geology of the icy crust. REASON will face some challenges. Europa's surface is not uniform, and the ice shell is likely to have significant variations in thickness and composition. There are areas where the ice is thought to be thinner, and others where it may be much thicker. This variability could make it difficult for the radar to penetrate to the same depth everywhere, as the ice's thickness and composition will influence how much of the radar signal is absorbed or reflected. The REASON team will need to account for these variations and adjust their analysis accordingly. Some salts might alter the way the radar waves travel through the ice, potentially complicating the interpretation of the data. The radar's dual frequency system is specifically designed to account for these factors, helping scientists differentiate between the radar reflections caused by ice, liquid water, and other materials. This will require sophisticated data processing and careful analysis to ensure that the results are as accurate as possible. But the radar system is not the only way Europa Clipper will explore the Moon. The spacecraft will also be carrying a variety of spectrometers that will analyze the chemical makeup of Europa's surface and atmosphere. One such instrument is the Europa Imaging System, or EIS, which will capture high-resolution images of Europa's surface in multiple wavelengths of light. These images will help scientists study the surface features in great detail, such as its complex patterns of ridges, cracks, and other geological formations. The spectrometer on board this system will help scientists decipher the composition of Europa's ice, looking for specific chemical markers that could hint at what lies beneath. In addition to EIS, Europa Clipper carries a suite of other spectrometers, including the Europa Ultraviolet Spectrograph, or EUVS, which will investigate Europa's thin atmosphere. The UV spectrometer will be able to measure the composition of the ionized gases surrounding the Moon, looking specifically for water vapor and signs of activity that could suggest an active subsurface ocean. This data will also help scientists track the behavior of plumes, which may be ejecting water and other materials from the Moon's ocean into space. The infrared spectrometer on board Clipper is critical for understanding the Moon's surface and subsurface. Using infrared light, this instrument will analyze the ice composition, looking for signs of different salts, organic compounds, and other chemicals that may indicate the presence of a subsurface ocean with chemical processes potentially similar to those on Earth. By measuring the specific wavelengths of light that are absorbed or reflected by different substances, scientists can determine the chemical and mineral composition of Europa's surface. To complement these instruments, Europa Clipper is also carrying a sophisticated magnetometer. The magnetometer will measure variations in Europa's magnetic field, providing key information about the Moon's interior and whether a liquid ocean exists beneath its icy crust. Scientists suspect that the magnetic field around Europa is influenced by a subsurface ocean that interacts with Jupiter's powerful magnetic field. By studying these variations, the magnetometer can provide clues about the depth and salinity of the ocean, as well as whether it is in contact with Europa's rocky core. The complementarity of these instruments is analogous to a detective using different tools to investigate a crime scene. The radar is like the detective's magnifying glass, revealing hidden layers and structures beneath the surface. The spectrometers, on the other hand, act like chemical analysis tools, revealing the molecular makeup of materials on the surface and in the atmosphere. The magnetometer, like a metal detector, helps confirm the presence of hidden oceanic features, offering another piece of evidence to support the overall investigation. Together, these instruments create a comprehensive set of tools that will allow scientists to probe deeper into Europa's secrets, from its icy surface to the potentially habitable waters below. Through its detailed radar surveys, chemical analysis, and magnetic measurements, Europa Clipper will explore whether the Moon could harbor life, or at least the conditions that could support life. These findings will be critical for future missions aimed at exploring Europa's ocean more directly, either by analyzing the plumes or by sending a lander or potentially even a submarine to the Moon's surface or beneath its icy crust. The SUDA experiment, hunting for ocean spray in the vacuum. The Europa Clipper's SUDA, or Surface Dust Analyzer, will play a crucial role in helping scientists understand what is happening on Europa's surface and in the Moon's plumes. Unlike many instruments that need to land or drill into a surface to collect data, SUDA uses a very different approach. It collects and analyzes tiny ice grains that are ejected into space. This gives scientists a way to study the surface without ever touching it. Europa's surface is constantly bombarded by radiation, and this bombardment can cause material on the surface to be kicked up into space, forming small particles that can travel far from the Moon. Some of these particles are launched into space by Europa's icy plumes, while others come from a process called sputtering, in which high-energy particles from space strike the surface and release bits of ice. These tiny ice grains are ejected from the surface and can sometimes be sampled by SUDA. SUDA's mass spectrometer works by capturing these tiny particles and analyzing them to identify their chemical composition. The mass spectrometer is able to detect different elements and molecules within the ice grains, which gives scientists important clues about what the surface material is made of and what might be hidden beneath. When SUDA samples a particle, it measures the weight of the atoms and molecules within it, and this data is then sent back to Earth, where it can be analyzed in great detail. The idea behind SUDA is that it can collect samples without having to land on Europa or drill into its surface. This is an important distinction because landing on or drilling into a moon like Europa comes with significant challenges. Europa's surface is covered in a thick layer of ice, which can be many kilometers deep. Drilling through this ice to reach the subsurface ocean would be an extremely difficult and risky task. The ice grains SUDA collects may contain vital information about the composition of Europa's surface and its ocean. For example, if the particles originate from Europa's plumes, they could provide direct evidence of the materials that are being transported from the subsurface ocean to the surface. This could give scientists insight into the ocean's composition, including the presence of salts, organic molecules, and other substances that could be important for understanding whether Europa's ocean is habitable. SUDA's role is particularly important when considering Europa's plumes, which offer a tantalizing glimpse into the Moon's subsurface ocean. The analysis of these plumes might reveal whether the ocean is chemically similar to Earth's oceans, which would be a significant finding in the search for life beyond Earth. The ability to capture and analyze particles while Europa Clipper is in orbit means that SUDA can sample the surface of Europa repeatedly during its flybys, offering a comprehensive dataset. The spacecraft will fly by Europa multiple times during its mission, and each time it passes close to the Moon, SUDA will have the opportunity to sample the ice grains in the Moon's exosphere. This means that SUDA can gather data from different regions of Europa's surface and at different times, allowing scientists to see how the Moon's surface and its plumes may change over time. One of the challenges of using SUDA is that the ice grains it collects are extremely small, often only a few micrometers in size. This makes it difficult to catch and analyze these particles. The instrument is designed with special collectors to trap the particles and direct them into the mass spectrometer. These collectors are finely tuned to ensure that the smallest ice grains are captured and sent to the spectrometer for analysis. Once the particles are inside the spectrometer, the mass spectrometer analyzes them by measuring their mass and identifying the elements and molecules they contain. Some of the ice grains might come from sources that are not directly linked to Europa's ocean. The ice particles that SUDA collects could be influenced by a number of factors, including solar radiation, the motion of Europa's surface, or even interactions with Jupiter's magnetosphere. As a result, scientists will need to carefully analyze the data to ensure they can accurately pinpoint the source of the ice and determine its relevance to the search for a subsurface ocean. The information gathered by other instruments on the spacecraft will help put SUDA's findings into context. Instruments like the Reason radar and the infrared spectrometer will all provide complementary data that can be combined with SUDA's measurements. This combination of data will give scientists a more complete picture of Europa's surface and subsurface. The Europa Imaging System, not just another camera. The EIS is far more than just another camera. It's a sophisticated suite of imaging tools designed to unlock the mysteries of Europa in ways that previous missions, like those of Voyager and Galileo, could not. While these early missions gave us essential snapshots of the Moon, they were limited by their relatively low resolution and by their flyby nature, which provided only brief and isolated glimpses of Europa's surface. The Europa Clipper's imaging system is specifically built for detailed and continuous exploration. Its combination of wide-angle and narrow-angle cameras allows it to capture the full picture of Europa's surface, providing both broad context and fine details. The wide-angle camera is designed to capture large sections of Europa's surface in a single shot. This ability to capture a broad view is crucial for understanding the overall structure of the Moon and its most prominent features. The wide-angle camera's resolution is much higher than what was available during past missions, offering a level of detail that will allow scientists to see features that were previously indistinguishable. The wide field of view also makes it possible to study the Moon's largest regions, such as its chaotic terrains and expansive ridges, giving researchers a sense of the Moon's broader geological history. But what truly sets the Europa imaging system apart is its dual-camera setup, which includes a narrow-angle camera with an even higher resolution. This camera is engineered to take detailed close-up images of smaller features on Europa's surface. The narrow-angle camera will capture intricate details of the Moon's icy crust, helping scientists to study the complex interactions between Europa's ice shell and the liquid ocean beneath it. Features such as cracks, ridges, and possible signs of tectonic activity will be visible in ways that were not possible with the less detailed images from past spacecraft. Lighting plays a critical role in how we perceive and analyze planetary surfaces. Different angles of sunlight can cast shadows and highlight particular features, allowing scientists to observe aspects of the terrain that would otherwise be hidden. By taking multiple images of the same spot from different angles, the EIS can provide a 3D view of Europa's surface, enhancing our understanding of its topography and geological structure. This technique allows researchers to spot features such as ice ridges and pits that may not be immediately apparent in a single image taken under a different lighting condition. In contrast to earlier missions, which provided us with relatively few images of Europa, the Europa imaging system will offer a continuous stream of high-resolution data throughout the mission. Earlier flybys were limited by their short durations and the fact that they only captured distant images of Europa's surface. These images offered only a rough idea of the Moon's general characteristics. For example, Voyager's famous image of Europa, captured during its flyby in 1979, gave us the first real look at Europa's icy surface, but the resolution was so low that it was difficult to see much more than large features like dark spots or bright streaks. Galileo's flybys in the 1990s and early 2000s provided a few more detailed images, but the spacecraft's camera was still limited by its flyby nature and by the fact that the resolution of the images dropped the farther away the spacecraft was from the Moon. Galileo's images also showed a surface covered in long fractures and intriguing geological features, but without the detailed resolution needed to understand how these features were formed or how they interacted with the underlying ocean. Clipper, in contrast, is not just passing by. It will make multiple close flybys, taking advantage of the spacecraft's ability to orbit Jupiter and get close to Europa on a regular basis. The spacecraft will pass Europa roughly 50 times during its mission, allowing it to capture images of the Moon's surface from many different angles and under different lighting conditions. The high resolution of the EIS will enable the spacecraft to zoom in on specific areas. The advantage of this constant, detailed coverage cannot be overstated. With its high-resolution imaging system, Europa Clipper will be building a comprehensive map of Europa's surface, giving us the most complete and accurate image of the Moon to date. Each image will add a layer of detail, allowing scientists to track changes in Europa's surface over time. Beyond surface features, the EIS will also play a crucial role in studying the interactions between Europa's surface and its environment. The EIS can track how radiation affects the surface over time, identifying regions where radiation-induced processes, such as the formation of unusual compounds or the degradation of surface materials, are taking place. By observing how the surface is altered by radiation, scientists can infer what materials are available for potential life in the ocean beneath. The high resolution and versatile capabilities of the Europa imaging system will also help to shed light on the Linei and the Lenticuli. Europa's surface is marked by an intricate web of fractures, ridges and faults, and the EIS's ability to capture the fine details of these features will be invaluable in understanding their origin and what they reveal about the Moon's internal dynamics. By comparing the surface features of Europa with those of other moons and planets, scientists can make more informed assessments of the Moon's capacity to harbor life. Subsurface biosignatures. What would life leave behind in the ice? The search for life beyond Earth has always been a quest to find signs, biosignatures, that something is alive or has once been alive. On Europa, one of the most exciting areas of research is understanding what kind of biosignatures might be left behind in the Moon's icy surface. Unlike Mars, where surface exploration has uncovered the potential for past water and even microbial life, Europa's potential for life is hidden beneath layers of ice, making the search for signs of life much more complex. Biosignatures are any chemical, isotopic, or morphological clues that indicate the presence or past presence of life. On Earth, life has left behind a variety of markers in the geological record: fossils, specific types of molecules, and certain isotopic ratios that indicate biological processes. Similarly, on Europa, life, if it exists or has existed, could leave behind similar types of markers that could be trapped in the ice. One of the most promising types of biosignatures to look for is lipids, fatty molecules that are essential to the structure of cell membranes in most known forms of life. Lipids are extremely stable and can remain intact for billions of years, making them excellent candidates for identifying signs of past life. If life ever existed on Europa, its cell membranes would likely have been made of lipids, and some of those lipids might still be preserved in the ice today. These lipids could become trapped in the ice as the ocean beneath freezes, potentially giving us clues about the types of organisms that might have lived there. The challenge for scientists is to develop methods sensitive enough to detect these microscopic organic molecules in the icy surface, where they may be buried deep beneath several kilometers of frozen water. Another type of biosignature that could be present in Europa's ice is the isotopic signature of life. Isotopes are variants of elements, such as carbon or sulfur, that have different numbers of neutrons in their atomic nuclei. Biological processes on Earth tend to favor certain isotopes over others. For example, carbon atoms in biological molecules tend to have more of the lighter isotope, carbon-12, rather than the heavier carbon-13. This is because the enzymes that drive metabolic processes in living organisms prefer carbon-12 when building complex molecules. In the case of Europa, if any biological processes have occurred in its ocean, we might find similar isotope ratios embedded in the ice, providing indirect evidence of life. Isotopic ratios could also help differentiate biological signatures from purely geological ones. For instance, geological processes might also affect the isotopic ratios, but these would follow different patterns than those caused by biology. If scientists can distinguish between the two, they would have a powerful tool for detecting past or present life on Europa. Organic molecules, including amino acids and nucleotides, the building blocks of proteins and DNA, could be formed through non-biological processes, such as chemical reactions driven by heat or radiation. However, if these molecules are found in patterns that resemble those produced by life, this could be a powerful indication that life once existed, or even still exists, on Europa. Once they are trapped in the ice, these organic molecules might be preserved for long periods, potentially giving scientists a way to identify them even after millions of years. Detecting these markers would require a highly sensitive approach, one that can distinguish between biological and geological materials, and also identify specific patterns associated with life. This is why the study of ice textures is so important. The way the ice forms, fractures, and changes over time could provide crucial information about whether life has existed there. In addition to physical biosignatures, Europa's ice may preserve evidence of biological activity in the way it is structured. As the ice shell shifts and moves, it could trap and preserve patterns that might indicate past biological processes. For example, certain microorganisms on Earth can leave behind characteristic patterns in ice, such as layering or distinctive microstructures in the ice crystals. It's possible that similar patterns could be found on Europa, indicating where life once thrived. While ice can act as a time capsule, preserving ancient organic molecules and other signs of life, it's also subject to a variety of forces that could alter or destroy any potential biosignatures. For example, radiation from Jupiter could break down organic molecules or alter their chemical structure. The pressure and temperature fluctuations beneath the ice could also affect how biosignatures are preserved. However, despite these challenges, scientists are hopeful that the deep, thick ice shell may offer a relatively stable environment where biosignatures could be safely trapped for a long time. Scientists are actively developing new techniques to analyze Europa's ice, both in orbit and on the surface. They are also exploring the possibility of drilling into the ice to directly sample material from the subsurface ocean, which could provide the most direct evidence of life. If life has ever existed on Europa, the biosignatures it left behind could be the key to understanding whether life is common in the universe or a rare occurrence. If Europa's ice does contain biosignatures, it would suggest that life could be more resilient and adaptable than previously thought, able to survive in some of the most extreme conditions in the solar system. Whether or not life exists on Europa currently, the discovery of biosignatures would be a groundbreaking step in our quest to understand the conditions that support life and how life might emerge on other planets and moons across the cosmos. Europa's sterilizing radiation. How deep must life hide? The radiation levels on Europa are strong enough to break apart molecules, damage cellular structures, and essentially erase any signs of life that might be near the surface. If life exists or has existed on Europa, it would likely need to be shielded from this environment in order to avoid being destroyed by the relentless bombardment of particles. The radiation from Jupiter's magnetosphere penetrates the surface of Europa at varying depths. It is strongest near the surface and decreases with depth. But even several kilometers beneath the icy crust, the radiation is still present, although it becomes less intense. The key question is how deep life would need to be to remain safe. For this, scientists use models based on the penetration depth of radiation and the amount of shielding required to protect biological molecules. Research suggests that the surface of Europa receives doses of radiation that would be lethal to most forms of life in a matter of days or weeks, depending on the level of exposure. Even bacteria, which are incredibly resilient on Earth, would have a difficult time surviving these conditions. To estimate the safe zone where life might still survive, scientists need to calculate how far radiation penetrates into the ice and what the threshold is for survival. The deeper you go beneath Europa's ice shell, the less radiation there is, because the ice acts as a shield. Studies suggest that life could potentially exist in a safe zone a few kilometers beneath the surface, where the radiation is low enough to allow organisms to live, provided other conditions, like heat, liquid water, and nutrients, are also available. If there are areas where liquid water exists beneath the ice, they might provide the kind of environment where life could endure. However, the ice itself, which is tens of kilometers thick in some places, would need to be thick enough to shield any potential organisms from radiation that might still penetrate down into the ice. The ability to study and sample the deeper layers of Europa's ice is critical for understanding whether life can hide in these safe zones. Current technology, like Europa Clipper, will allow scientists to study the surface in great detail, but direct sampling of the ice itself will likely require the development of specialized equipment in a future mission. In terms of the radiation environment, the safe zone is generally considered to be a few kilometers below the surface, but the exact depth depends on factors like the intensity of radiation at any given time, the local variations in Europa's ice shell, and the potential for cryovolcanic activity or other processes that might alter the depth of safe regions. The radiation dose decreases quickly with depth, but even at depths of several kilometers, it is important to understand that life would still need to be protected from the radiation to survive. Europa's ice shell is made up of layers of water ice, some of which might be more porous or fractured than others. This variability means that the amount of shielding from radiation could vary depending on the exact location. This variability could create areas where life might be able to find refuge in deeper layers of ice, protected from the intense radiation above. Alien microbes or prebiotic soup, models of life's emergence. One prominent theory of life's origin on Earth is the RNA world hypothesis, which suggests that life began with simple molecules that could replicate themselves like RNA. This idea proposes that before the complex DNA-based life we know today, the first forms of life were built around RNA, a molecule that, like DNA, can store genetic information and catalyze chemical reactions. The RNA world theory is appealing because it explains how early life could have formed without the need for complicated cellular structures. Instead, RNA could have been the first self-replicating molecule, enabling life to evolve into more complex organisms over time. On Europa, such a process could be possible if the ocean contains the necessary chemical ingredients and the right environmental conditions. Water serves as the solvent for chemical reactions and provides a stable environment where complex molecules can form. It also helps transport chemical compounds, such as amino acids and nucleotides, that could form the building blocks of life. In theory, if these molecules were present in the ocean and could be combined in just the right way, they might form the first simple organisms, or at least the chemical precursors for life. But where would these molecules come from? And how could they form in the harsh conditions beneath Europa's icy crust? Some scientists propose that life on Europa could have emerged from a process similar to the one that is believed to have occurred on Earth, mineral catalysis. In this theory, life could have formed in the ocean through interactions between the water and the minerals at the bottom of Europa's seafloor. The seafloor of Europa, much like Earth's, could harbor hydrothermal vents, which could provide the necessary energy for chemical reactions to occur, with minerals acting as catalysts to speed up these processes. Minerals have been shown to play a critical role in helping simple molecules form more complex ones. On Europa, these minerals could facilitate the formation of key organic molecules, including amino acids and nucleotides. Another idea is the possibility that Europa could contain a form of life based on alternative biochemistry, one that does not rely on carbon-based molecules. This theory proposes that life could exist in forms that are radically different from what we know, using different elements or chemical processes to sustain themselves. If this type of life were to exist, it could look completely different from anything on Earth, and our methods of detecting it would need to be adapted. In this case, life on Europa might not be based on carbon at all. Instead, it could involve silicon-based or other non-carbon compounds, with chemical processes tailored to the specific conditions of Europa's ocean. The possibility of life being based on entirely different chemistry raises the stakes for exploration. Instead of looking for organisms that resemble the ones on Earth, we would need to rethink how we identify signs of life altogether. This would require new detection methods that could spot unconventional biochemical signatures. However, even if no such life exists, the raw materials needed for life might still be present in the ocean's depths, offering the potential for life to emerge in the future. Aside from microbial life, another consideration is the possibility that Europa's ocean may not be the cradle of life itself, but rather a chemical prebiotic soup, a mixture of molecules that could eventually give rise to life. This theory suggests that while life may not have started on Europa, the ocean could still contain a rich array of organic molecules that serve as the building blocks for life. These compounds could be formed through chemical reactions between water, minerals, and energy sources like heat or radiation. Over time, some of these molecules could evolve into more complex forms, possibly leading to the development of life. In the prebiotic soup scenario, Europa's ocean could act as a chemical factory, with the necessary ingredients for life present in large quantities. The ocean could provide a unique environment where organic molecules like amino acids, lipids, and nucleotides could form spontaneously, driven by energy from the Moon's interior or from external radiation. These molecules could then react with one another, forming larger and more complex compounds, eventually leading to the formation of self-replicating molecules that could kickstart the process of life. However, whether the ocean is capable of producing enough complexity to form life remains a critical question. While scientists can simulate the conditions of Europa's ocean in laboratory settings, it's difficult to replicate the exact conditions of the Moon's deep ocean. The pressure, temperature, and radiation levels are all far different from what we experience on Earth, and these conditions could greatly influence the types of chemical reactions that occur. It's also unclear whether the energy sources in Europa's ocean are enough to drive the kind of chemical reactions that could lead to life. Even if life does not emerge on Europa, the search for prebiotic molecules is still an important scientific endeavor. Finding chemical precursors in Europa's ocean would provide insight into how life might emerge in similar environments, such as the moons of Saturn or exoplanets that may harbor oceans beneath their icy crusts. It would also provide clues about the conditions necessary for life to exist, deepening our understanding of the factors that make a planet or moon habitable. The search for life on Europa will require innovative techniques and new ways of thinking about life, as well as a willingness to entertain the possibility that life could look radically different from what we know on Earth. Whether life has ever existed or is still present on Europa, the search for its origins could provide profound insights into the nature of life itself and its potential existence elsewhere in the universe. Robots before boots. Why drilling into Europa is a far future dream. The idea of sending a mission to Europa that can drill through its thick, icy shell and explore the hidden ocean beneath is a dream that excites many in the scientific community. However, this kind of mission is still very much in the distant future. Despite our ever-increasing technological capabilities, the engineering challenges of getting through that much ice are formidable. The ice shell is not uniform. In some areas, it is thinner, but in others, it could be as thick as 30 kilometers. That means that, in order to reach the subsurface ocean, any drilling or melting system would need to be capable of penetrating vast stretches of frozen water, an extremely difficult task. To make matters more complicated, this ice isn't just a solid block, it's dynamic. Europa's ice shell is believed to be in constant motion, with parts of it breaking apart and shifting. This means that drilling through the ice wouldn't be as simple as just reaching a stable, stationary layer. It would be more like trying to drill through a moving and shifting mass. The second major challenge is the environment in which any such mission would operate. Temperatures can drop to around -160 degrees Celsius, and any spacecraft or drilling equipment sent to the Moon would need to be able to survive these extreme conditions without its instruments freezing. But that's just the surface. Below that, as you go deeper into the ice shell, temperatures can vary depending on where you are. While the ocean beneath might be relatively warm due to tidal heating from Jupiter's immense gravitational pull, drilling through kilometers of ice would expose the equipment to harsh cold, potentially freezing the instruments or causing them to malfunction. Even if the temperatures could be managed, the radiation environment around Europa is another factor to consider. Even though Europa's thick ice layer offers some protection from the radiation, it still poses a challenge for any long-term mission on or around the Moon. Instruments would need to be shielded to withstand the harsh radiation for extended periods of time, adding complexity and weight. On Earth, drilling through ice is challenging enough, but doing so in the vacuum of space, with all the added complexities of Europa's environment, would require entirely new methods and materials. One idea that has been proposed is to use a heated probe that would melt its way through the ice. This method has been used in some Earth-based drilling operations, such as those in Antarctica. but scaling it up for use on Europa presents serious engineering challenges. For example, a heated probe would need to generate a tremendous amount of heat to melt through the thick ice, and that heat would need to be constantly replenished, as the probe would inevitably cool as it moved deeper into the ice. Ensuring the probe would have enough power to keep melting as it descended, without overheating or freezing, would require advanced thermal management systems. Mechanical drilling, on the other hand, would involve using a rotating drill bit to physically break through the ice, similar to how oil rigs drill through Earth's crust. However, on Europa, this method would be complicated by the nature of the ice itself. The ice is likely to be very hard and brittle in some places, while other regions may contain slushy or porous ice. The variability in the ice's texture would make it difficult to design a drill that could consistently perform in all conditions. Additionally, the drill would need to be incredibly durable to withstand the immense pressure at the depths of Europa's ice shell, as well as any potential movements of the ice itself. As it stands, the technology simply doesn't exist to drill through kilometers of ice on Europa. Instruments like radar can give us a sense of the ice's structure, while mass spectrometers will be able to sample particles in the plumes of water that might erupt from the Moon's surface. But for now, this is as close as we can get to understanding Europa's ocean. There are certainly ideas on the drawing board for future missions that might be able to penetrate the ice, but these concepts are still in the early stages of development. Some of the ideas include sending a lander equipped with a drill, but this concept would face the same challenges: how to survive the cold, how to power the system in the harsh radiation, and how to safely and effectively drill into kilometers of ice. Another option being considered is using a robotic probe to melt its way through the ice, but that would require a level of precision and sustained power that has not yet been achieved in spacecraft design. The lack of an immediate drilling capability doesn't mean that exploration of Europa's ocean is out of the question. Rather, it means that we need to take a different approach. Current and upcoming missions are providing us with crucial information that can help us understand the Moon. With these tools, scientists can begin to map out where drilling might be most effective in the future, and perhaps discover natural features such as ice fractures, plumes, or thin spots in the ice that could make the task of reaching the ocean easier. Europa Base. Alpha. Could humans ever live on or beneath the ice? Could we ever build a base on or even beneath the icy surface of this moon? The challenges are enormous, but the dream is not entirely out of reach. Europa is one of the most promising places in the solar system for finding life beyond Earth. And someday, people may want to be there in person, not just looking from orbit, but living and working directly on the Moon. A person standing unprotected on the surface would receive a lethal dose in just a few hours. That means any human base would have to be heavily shielded. One way to solve this is by burying the base under meters of ice. Ice is actually a good material for blocking radiation, especially when it's packed thick. By carving out tunnels or chambers beneath the surface, astronauts could stay safe from the worst of Jupiter's radiation. But getting under the ice in the first place wouldn't be easy. Ridges and cracks crisscross the landscape, and in some places, frozen blocks of ice the size of buildings are tilted or piled up. Landing a spacecraft in this environment would be risky. A flat, stable area would need to be found, or perhaps smoothed out in advance by robotic missions. Once on the surface, getting below it would take time and energy. Melting or digging into the ice might take days or weeks, depending on how deep the astronauts would need to go to stay safe. Building a base would also require a reliable power supply. On Earth, or even on Mars, solar panels can work well. But Europa is far from the Sun, nearly 5 times farther than Earth, and the sunlight there is weak. Add in the fact that the base would probably need to be under ice or in shadow most of the time, and solar power becomes a poor option. That leaves nuclear power as the most likely choice. Small fission reactors could be used to supply a steady flow of electricity, keeping the lights on, powering heaters and supporting life support systems. These reactors would need to be compact and safe, designed to work for years without maintenance. Just like on the International Space Station, a base on Europa would have to recycle air, water, and waste. There's no atmosphere on the Moon, so everything would have to be brought in or reused. A closed-loop system would allow astronauts to breathe the same air over and over, with machines scrubbing out the carbon dioxide and adding back oxygen. Water could be melted from the ice, assuming it's clean enough, or brought along from Earth in tanks. Food would be more complicated. Growing food on Europa would be harder without natural sunlight, but artificial lights could help hydroponic plants grow in underground greenhouses. Communications would be slow. Because Europa is so far away, it takes about 30 to 50 minutes for signals to travel between Earth and Jupiter, depending on where the planets are in their orbits. That means real-time conversations aren't possible. For that reason, astronauts on Europa would need to be able to work mostly on their own, without waiting for instructions. They'd also need to send data back to Earth through orbiting satellites or relay stations, which would keep the connection stable and reduce delays as much as possible. One idea that might work in the near term is to control robots from orbit. Rather than land humans on Europa right away, we could put astronauts in a spacecraft orbiting the Moon and have them operate surface rovers and drones in real time. This way, they'd avoid the radiation and surface hazards, but still be close enough to perform science and explore. This kind of teleoperation would be much faster than trying to send commands from Earth, and it would let humans respond quickly to surprises, like a sudden plume eruption or a strange object on the ice. But teleoperation isn't the same as being there. To truly understand Europa and to look for life in its ocean, scientists may eventually need to be on the surface or even under it. This is where the dream of a permanent base comes in. Some researchers imagine a small, pressurized station buried beneath the surface, heated and lit by nuclear power, with labs, sleeping quarters, and even a garden. Others imagine a mobile station, a kind of ice crawler that could move slowly across the landscape, stopping to drill into the ice and take samples. There are even more futuristic ideas. Some think about thermobots, or heat-based probes that could melt their way down into the ice while sending back data. A human base might include such a probe as part of its operations, guiding it as it descends into the unknown. In theory, a probe like this could carry a small submersible, something that would break through into the ocean and swim around looking for signs of life. That's still many decades away, but if the base is there, it could be the launch point for that next step. Living on Europa would also require careful planning about human health and safety. The gravity on Europa is only about 13% of Earth's, so astronauts would experience weak pull on their bodies. Over time, this could lead to muscle and bone loss. Regular exercise would be essential, and future habitats might include rotating rooms or other equipment to simulate gravity through motion. Medical support would also need to be on board. In such a remote place, help would be months away, so the crew would need to handle emergencies, injuries, or illness on their own. Being so far from Earth, in a cold and lonely place with no natural light and only a small team for company, would be tough. The base would need to include social spaces, light therapy, and ways to stay mentally active and engaged. Communication with family and mission control, even if delayed, would help keep the crew connected to home. The design of the base, making it feel more like a home and less like a machine, would also make a difference. Eventually, if humans could live safely on Europa for extended periods, it might change the way we explore the outer solar system. Bases like this could serve as stepping stones to even more distant missions, to Ganymede, Callisto, or the icy moons of Saturn. They might also allow for deeper science, with humans conducting experiments, guiding robotic probes, and possibly even diving into Europa's ocean themselves one day. But all of this depends on solving some of the biggest engineering problems humans have ever faced. Power, radiation, ice, isolation, and distance all must be overcome before we can seriously consider building a home on Europa. For now, orbiters and flybys will teach us more about the Moon and help us find the best spots for future exploration. The dream of Europa Base Alpha may still be far away, but each mission we send brings us one step closer. If we find life, then what? If we ever find life on Europa or anywhere beyond Earth, everything changes. That single discovery would not just be a scientific headline, it would be a turning point. Suddenly, the mission is no longer only about learning what's out there. It becomes about how to act, how to protect, and how to decide what comes next. The search for life has always carried the hope of finding something. But once we do, the question becomes what we are allowed to do about it. Right now, spacecraft that go near Europa, or anybody that might support life, follow strict rules. These are called planetary protection guidelines. They're set by international agreements and shaped by decades of science. The idea is simple. Don't bring Earth germs to another world, and don't bring alien germs back home. In practice, this means every bolt, wire, and instrument on a spacecraft has to be cleaned carefully. Engineers bake parts at high heat, scrub them in special solvents, and build spacecraft in sterile cleanrooms to remove as many microbes as possible. Even then, nothing is ever 100% clean. Some hardy Earth microbes can survive in harsh conditions, cold, dry, and low in nutrients. If we accidentally drop them on Europa's surface, they could, in theory, sink into the ice or get carried into the ocean over time. And if there's life down there already, that life could be threatened. We don't know how it would react. Would it be fragile? Would it be able to fight off invaders? Would it even recognize Earth life as something living? These are questions that we can't answer unless we find that life. But that's also the problem. We don't want to find it by harming it. That's why any future mission that might touch liquid water or even drill deep into the ice has to follow even tighter protection rules. Europa Clipper will not land, thus reducing the risk of contaminating the surface. Later, however, if we do send a lander, it will need to be the cleanest machine ever built. Every surface that touches Europa's ice must be sterilized. The drills and scoops must be free of DNA, bacteria, and organic particles. Even then, the mission will be designed so it doesn't get near areas most likely to host life, at least not at first. But what happens after we find life? If we detect certain molecules in the ice, things like lipids, amino acids, or repeating structures in organic material that suggest biology, we'll need to slow down. Scientists will want to confirm the data. They'll need more flybys, more instruments, maybe even new spacecraft. We can't assume we've found life until we're sure. But while that process unfolds, the rules for exploration will likely tighten. New policies may be written. Nations may debate who has access and who doesn't. Space agencies may be required to pause all missions that could pose a risk. While most scientists agree the chance of harmful alien microbes is low, it's not zero. If we someday bring samples back from Europa or anywhere with signs of life, they'll have to be quarantined. Not just in a box, but in special labs with multiple barriers, filters, and emergency systems. Everything that touches the samples will be tracked. The air, the water, even the scientists working nearby will be monitored. We don't know if Europa's life would be dangerous, but because we don't know, we have to assume it could be. Then there's the moral part. If Europa does have life, even if it's just simple cells floating in the ocean, do we have the right to study it up close? Should we try to interact with it? Should we try to protect it like a nature preserve? On Earth, we try to protect endangered species and untouched ecosystems. Some people believe we should do the same for alien life, leave it alone, observe from a distance, and avoid causing harm. Others believe that exploration means interaction. If we don't try to learn more, we'll never understand how life works beyond Earth. But what if Europa's life is more complex than we expect? What if, somehow, we find something that moves with purpose, or reacts in a way that feels intentional? Suddenly, we're not just talking about microbes. We're facing the possibility of intelligence, even if it's at a very simple level. And then the rules must shift again. Interacting with something that may have its own form of awareness or survival instincts would force us to reconsider what alien means. It wouldn't be science fiction anymore. It would be real and possibly irreversible. Even if the life we find is prebiotic, just molecules that are on their way to becoming living systems, it's still important. Prebiotic chemistry is rare and fragile. It could be part of the same process that once led to life on Earth. Studying it means walking a thin line between learning and disturbing. A single drill or a heated lander might destroy patterns that took millions of years to form. That's why missions to places like Europa will likely remain robotic for a long time. Machines are easier to clean, easier to control, and can operate without breathing or eating. Human missions are far riskier for contamination. And so, even if we dream of walking on Europa someday, the presence of life there might make that dream much harder to justify. If life is found, who gets to announce it? Who confirms it? What country, what agency, or what group of scientists? In the past, mistaken claims of life in space have created controversy and confusion. The rules for how to handle a confirmed detection aren't fully in place. Scientists have discussed the idea of a kind of code of conduct for life detection, how to verify results, how to share them, and how to include the public in the process. But until a real case happens, these plans are only ideas. The discovery of life would also change how we build future missions. Some destinations might become off-limits to protect fragile ecosystems. Others might require international cooperation, shared data, or limits on the kinds of experiments allowed. The search for life could become something that no one country is allowed to pursue on its own. Instead, it might be managed like a World Heritage Site, with agreements that balance science, ethics, and caution. And beyond all that, there's the public reaction. Life on another world, no matter how simple, would be a cultural moment. People might feel hope, fear, wonder, or responsibility. The way people respond could shape the next steps of exploration. There may be calls to go faster to find out more, or there may be calls to stop to protect what's been found. Either way, it won't just be a science story. It will be something that affects how we see ourselves and how we act in a much larger universe. So, what are your hopes for what we discover on Europa? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.